This is a full-bodied car, 9.1, 154 miles an hour through a 5-speed stick shift, independent rear end, and it would pull wheel stands. It needed a parachute to be allowed to turn up at the racetrack. This is a car that was bought for $3,000. It never owed me more than $12,000.
Welcome to the HPA Tuned In podcast. I'm Andre, your host, and in this episode, we're joined by Ben Diggles from Diggles in Australia. Now, Ben is actually a personal friend of mine. I've probably known him for upwards of 20 years now. He used to actually be a customer in my old tuning shop before he moved across the ditch back to Australia. Now, he's a little unique in terms of the guests we normally have on this show, given that he is a marine biologist. He actually has a PhD, and his day job is essentially fixing sick fish. That being said, he is still one of the smartest people I know when it comes to engine building and engine tuning, specifically in very high output circumstances such as import drag racing. Ben is well known for his work with the Nissan FJ20 turbo engine, quite an old engine design now coming out of the 70s. His own S12 Gazelle still holds the world record as the fastest Gazelle on the quarter mile with a 9.1. However, he wanted to go deeper into the FJ20 and see what it was really capable of, and he and his uncle actually put one into a rear engine dragster and went into the high sixes. And this is where the fun begins, because he started to learn all sorts of things about combustion stability, and abnormal types of combustion such as knock, super knock, and pre-ignition that you don't generally start to see problems with until you're really pushing these engines as hard as he did. This really led to him going deep down the rabbit hole of studying these forms of abnormal combustion, and he's got more knowledge on this topic than most people. I'll admit, this particular episode goes long. It is the longest one we've brought out, and it is super tech heavy. But if you are interested in learning more about what goes on inside the engine, what goes wrong inside the engine, and most importantly, how we can prevent that, this is the episode for you. There are some absolute nuggets of gold in here, and I guarantee you're going to need to rewind and listen to this one a couple of times. Before we get into our interview though, quick introduction to HPA for those who haven't been involved in our podcast so far. High Performance Academy is an online training school. We specialize in teaching people how to tune, how to build race engines, how to construct wiring harnesses. We also cover topics on race driver education, race car setup, data analysis, and fabrication. All of our courses are delivered via high-definition video modules that you can watch from anywhere in the world, provided you've got an internet connection. If you want a full list of our courses, you can head to hpacademy.com/courses, and as a podcast listener, you can use the coupon code podcast75, and that will get you $75 off the purchase of your very first HPA course. We'll put a link in the description to our courses as well as that coupon code. All right, let's get into our interview now. All right, Ben, welcome to the podcast. Thanks for joining us today. And like we do with all of our guests, let's start by getting a bit of a sense of your background, specifically how and when did you develop an interest in cars?
Thanks, Andre, for inviting me today. I think cars for me are a bit of a misspent youth. I was exposed to them from the word go. Dad was always involved with whole British MGs, and there was always something happening in the bottom of our house, I suppose, where we lived. But Dad and his mates, which included my uncles, they were actually heavily into drag racing in Australia in the 60s and the 70s, which is the early days of drag racing here.
So you pretty much had no chance, really, did you? Predisposed to become a drag racer?
It depends on what you like doing, I suppose. I do like fishing and other things which have sort of moved me in various different paths, but that exposure to people pulling cars apart from the very early age. I don't know whether a lot of the listeners have actually worked on older British cars, but they are constantly being pulled apart and leaking oil and doing other things like that. So it was just something that I grew up with, but I got some of the earliest memories were attending some of the drag strips in the late 1970s with my uncles. They were racing various sort of cars, but the one that I remember was a little dragster called Badger, and it had a little Datsun 1.8 litre engine in it, running naturally aspirated 10-second quarter miles, 1978, 79.
That's actually pretty impressive for that era. Is that why you were sort of led down the path of the Datsun/Nissan passion, and more specifically, you seem to have gravitated towards the FJ20 turbo engine?
Yeah, that is a fair call. I guess my uncles moved through, and Dad stayed with the British stuff. My uncles moved through various permutations of the four cylinders that were available at the time. And in the 70s, of course, Nissan were quite prominent and successful in rallying and road racings with that L series engine. I think the L series started out with the Datsun 510 series, the 1600s in the late 1960s, and also 240Zs, 260Zs. And so they had quite a racing heritage in the 70s in those areas, but not so much obviously at the drag strip. The drag strips dominated in those times by the V8s. But obviously good sound basis for reliable horsepower. And you used to be able to get these books called How to Hot Rod and Race Your Datsun. And I think having that information available and looking at the various platforms, they were the ones that uncles chose. And 10-second quarter, even today, in a natural aspect all motor sort of class, is no joke. Like the safety standards for the cars back then would mean you could never build anything as light today as they were running back then and be allowed on the track. But that sort of basis. But again, there are other really cool things happening in the early 1980s in relation to touring cars. And in Australia, for example, one of the coolest little touring cars was a little turbo Bluebird that we well remember beating the V8s in our Bathurst race in 1984.
And that was the Z18 turbo engine, am I right?
Yeah. So there's the Z18 turbo engine, a little 1.8 turbo 4. So all of those sort of things led to, a gravitation towards that Nissan brand for my uncles, and we were watching on. Group A racing was when 85, 86 is when actually that Nissan FJ20 engine first came out in the DR30 Skylines. That formed the basis of, some of Australia's first real sport compact drag racing cars, which was my uncle Jeff Watson's Austin Healey Sprite, which again, it started with that Z20 engine. That was a 2-litre Z-based Nissan engine running in the 10s with a supercharger. But when he changed over to that FJ20 platform, and this would be probably in the early 1990s, mechanical injection, but with a turbocharger, all of a sudden he was breaking records, knocking off people like Victor Bray.
Let's park that side of the conversation for a moment because I do want to focus on it. But just before we jump ahead, I just want to quickly cover off your professional background because you're a bit of an outlier in terms of our podcast guests so far, in that you're actually involved in anything but the automotive industry from a professional standpoint. So can you just briefly tell us what you actually do for a living?
Okay, well, I must admit I'm a hobby tuner. What I do for a living these days is I'm a marine biologist who specialises in the health of aquatic animals. So I'm a fish doctor. So it is, it's a bit different, but mind you, there's lots of blokes around the world who are interested in both cars and fishing. I meet them all the time.
Sure. Given your sort of tertiary education level, getting a doctorate there, having my own sort of experience with university here in New Zealand, I kind of find that tertiary education really, how would I put it, teaches you how to learn and how to think a little bit differently. And I know that you're incredibly analytical when it comes to the performance of an engine, in an area that I don't know too many other people that analyze engine performance in the way that you do. Do you think that's sort of a crossover from how your mind works as a result of your tertiary education?
The tertiary education, in some respects, it shows the way to being able to find information. Being able to process it can be something that I think some people have that ability and some people may not necessarily. They may be able to learn it, but it's not something that they innately find easy to do. So from my perspective, it's probably, one of Australia's first eminent scientific people in Australia was my great-great-grandfather, who came here in the 1850s. And he set up the Queensland Museum and a few other things there. It's probably genetic from the point of view of that side of things. But the university was in relation to cars, I mean, I needed to be able to drive to and from university, and with the Nissan side of things, so you'd buy a $500 Datsun to get to and from university, and you needed to know how it worked to stop it breaking down. So that's the practical side of how the cars fit in there. Basically, practical people. I was the first person in my family to go to university.
Okay. Well, I guess for our listeners, it's probably refreshing to hear that you don't have to become a microbiologist in order to learn how to build performance engines, which is probably great. Not a lot of crossover there, perhaps. Anyway, okay, let's move on. And you've started talking quite a bit here already about your uncle Jeff Watson, and I know that this is a name that is definitely not going to be familiar to the majority of our listeners outside of Australia and New Zealand. I remember when I was probably first getting involved in cars, and back at the time, one of the magazines, obviously the internet really wasn't a thing back then like it is now, so you were forced to read car magazines to keep up to date with what the cutting edge technologies were, who was doing what, and what records were being broken. And that little Austin Healey Sprite powered by the FJ20 turbo engine, that was making headlines back then. And in particular, I seem to remember one magazine that featured, I think he had taken down Victor Bray, and again, that's a name that no one outside of Australia and New Zealand is probably going to recognise, but a very big name in the door slammer racing right up to today. I believe he's still operating, or maybe his son now, Ben Bray. But anyway, I digress. And this little Austin Healey Sprite with a little 4-cylinder turbo engine had taken down Victor Bray's door slammer in a heads-up drag race. I think 7 out of 8 attempts or something like that, which just unheard of stuff. So obviously a big name, and he was really doing some things well ahead of his time. Can you sort of give us your impression of what he was doing back then and how you've sort of learned from his exploits?
The thing is, back there, they were racing in superstock, which more a horsepower per cubic inch class, because they had the weight brakes for the various engine types. And so the big supercharged V8s would have a certain weight brake. The 4 cylinders with the forced induction would actually have to carry a lot more pounds per cubic inch. But even then, still then, so you're racing on a class handicap record, and so they actually weren't heads-up races. But this car, back in the early 1990s, was running 8.1s, 160 miles an hour in a car with a 90-inch wheelbase. And to see that little Sprite take down those big supercharged cars, it was really something to see. It leaves quite a impression on young blokes who are interested in cars.
Yeah, absolutely. And my apologies, not heads up, but however he was winning against some of these bigger capacity supercharged V8s, still an impressive achievement. Moving forward a little bit, sort of how I got to know you was back when you were living in New Zealand, and back the time sort of when I was drag racing my Evo, and you actually were a customer of my old shop with your Datsun 1600/510 and then the S12 Gazelle that you built up as a drag car. So let's talk about that Gazelle, because as I understand it, that actually still holds a world record for the quarter mile performance. So why go down the path of that S12 Gazelle? What sort of drew you to that? I mean, I'm not admittedly a Datsun/Nissan guy at heart, but it doesn't seem like maybe the most obvious choice to start building a drag car out of.
Yeah, well, the backstory is, I guess, I moved countries to New Zealand in the mid-90s. With my Datsun, by that stage, aftermarket EFI was just taking off. I mean, the secret to making horsepower in these little engines is being able to control them properly. And remember, in the 80s, before EFI was widely available, we were using carburetors, and that's something that I cut my teeth on SU carburetors or the Hitachi versions, the Japanese versions. But you're reading in these magazines that you talked about these EFI engines, which were the gateway to increased power and reliability but you couldn't necessarily, you were really restricted by the factory ECU. But then these aftermarket ECUs became available where you could actually tune these things. And so I actually put a naturally aspirated FJ20 in my 510. And that's what I actually had when I brought it over to New Zealand. And I think you got to know me in the process of putting a turbocharged version of that engine in the 510, which went pretty well. We ran down into the low 12s, and I think it was actually pretty hard to beat in that little green Datsun. We won the inaugural Import Drag Racing Championship, remember, in that car, early 2000s. So the Gazelle, the S12 Gazelle, is actually a factory. These are all engine conversions that we were doing. But the S12 Gazelle is the factory-fitted FJ20 turbo car, which was only available in Japan. And for someone like me living in this part of the world, that's a real novelty. We don't get to see very many of these factory FJ20 turbo fitted cars. I think there was a Skyline or that. And one actually came up for sale, and the bloke lived in my street.
Match made in heaven.
Yeah, it wasn't running. The car wasn't running, but it did have clapped out FJ turbo engine in it and a roll cage. So to me, that was as good an excuse as any to buy that platform. I had no idea how it would translate to as a drag car, but it was actually set up as a more multi-purpose thing. We run it around racetracks as well. So it was just another interesting project that allowed me to fiddle a bit more with that FJ20 engine.
All right, so what did you sort of learn over the time of playing with that FJ20? I mean, we'll talk about your next foray, which got a little bit more serious with the FJ20 as well. But I mean, up to this point, you're sort of not setting the world on fire in terms of your power aims with the engine. What's the basic architecture of that FJ20 engine like? I mean, for anyone who's seen one, it's the size of a small car, essentially. These things look like they're built out of blocks. They're massive, and hence, on face value, they look like they've been an incredibly strong engine to start with. I mean, it's a relatively modern design in terms of 4-valve cross-flow, a step up from the earlier generation of the Datsun engines. But yeah, what's the good, bad, and ugly about the FJ20?
It's a 4-valve, 2-litre 4-cylinder engine that are essentially designed by Nissan probably the late 70s or indeed the early 1980s for rally racing. And remember, this was leading up to Group B rally. And originally that FJ series engine came out as what's called a FJ24, a 2.4-litre naturally aspirated rally motor with carburetors that was running in the 240 RS rally cars that, of course, got completely wasted by the four-wheel drive Audi Quattros, Peugeot 205s, and all those other things that came along. Remember, the 80s was just an amazing time for engine development when these EFI systems came in and you could start to control these little engines and put turbochargers on them. And so Nissan just missed the mark there, staying naturally aspirated rear-wheel drive with the 240 RS platform. So they had to make something out of the investment they had in this engine. So my understanding is they converted them and started putting them in Skylines and Gazelles to sell them basically a D-stroke version down to 2 litres. So a smaller bore and a smaller stroke. And the cylinder head was redesigned, and they brought out this, definitely Nissan's first EFI 4-valve engine, but it may actually have even been the world's first sequentially injected 4-valve 4-cylinder. So it was quite something at the time.
So you sort of alluded to this era where there was a transition from carburetors to EFI, which I'm very fortunate that I didn't really get involved in cars. I missed that. and I'm not unhappy about that in the slightest. But so, I mean, I already know the benefits of EFI, but I mean, how much of a game changer was this, both the OE manufacturers as well as, of course, the aftermarket in terms of the control we had, even with those pretty prehistoric systems now? And then the advent of the aftermarket EFI systems starting to come online around that time as well to allow you to actually make tuning changes.
The thing is, these motors in the early 80s, they were still developed basically through rule of thumb. There'd be no CFD analysis. There's not a lot of, I guess it'd be closely held information that the manufacturers had themselves and in their racing teams to develop these engines. But when you look at that FJ20, for example, they chose a really quite a wide included valve angle. It's around 75 or 80 degrees. It's more like they chose to replicate a 1960s Coventry Climax type engine.
Let's just dive into that term, the included valve angle. Unfortunately, we don't have the benefit of images to really simplify this, but can you explain what that term means and how that impacts the design of the cylinder head?
Okay, so if we imagine you have a spark plug sitting right in the middle of a cylinder pointing up and down vertically, and then you put a valve vertically right next to it, so parallel to the spark plug. That would be 0 included valve angle. The valve is actually vertical. So as soon as you start canting that valve so that the valve tip is moving away from the spark plug center line or the center line of the bore, you've started to increase the valve angle. And a lot of the empirical engine design work that was done in the 50s, 60s, 70s, and I think Duckworth was the first guy to realise that, these really wide valve angles that you used to see in a lot of the old Jaguars, the British stuff, 70, 80, even some of them probably almost 90 degrees, where you basically 45 degrees each side of your spark plug and the valves canted sideways. That's not necessarily, it looks good and can improve flow into the port, but it's not necessarily the best thing for combustion. And I think a lot of those hard lessons were actually learnt by the F1 guys. I mean, Coventry Climax did write something in the 1960s about when they went from their 2-valve engine. It worked quite well as a 2-valve, 2-litre engine, making about 200 horsepower back then at 10,000 RPM, and it was in some of the Coopers, I think, or early Lotuses. Then they went to a 4-valve version of that and were actually quite disappointed because they retained that wide valve angle, and they thought at the time that they lost some of the swirl that was related to the 2-valve aspect. But again, at that stage in the 1960s, they're hypothesizing. A lot of these engines were designed empirically based on carburetors or early mechanical injection. They didn't
got no software tools at hand to actually validate virtually the performance of a certain design before anything's actually manufactured, correct?
Yeah. So they're doing this empirically through basically shaping metal and trying it and then measuring and seeing how they're going. And it's a big hit and miss.
Incredibly expensive and time-consuming process compared to how things are done in the modern era.
Yeah, and so it's hit and miss, and there were more misses than hits in a lot of those times. And I think a lot of that came to a head in the 1980s when you start magnifying what are essentially, we'll probably talk about a bit later, these are combustion problems related to mixture preparation in the cylinder.
Absolutely. Yeah, it's an area that we're going to spend a fair bit of this podcast talking about because I think it is so critical, so important, and yet also highly overlooked by the enthusiast market anyway.
Well, we've forgotten how we've got to where we are now because a lot of those problems of those early engines have been engineered out. And I think the 1980s was an area there where they really started to take big leaps forward in that area. But Nissan, I think, were lagging a little bit by basically sticking to a 60s design on that cylinder head. Looked great. And from the rally perspective, it actually performed quite well. I think they were getting over 100 horsepower per litre out of the car. That's about 1.6 horsepower per cubic inch on carburetors. And that was obviously for a road car.
That's no joke.
No, it's a firm basis for a platform. And those Nissans also did quite well in Group A racing with the turbocharger attached. But in comparison to what we ended up doing later on with our development in this side of things, they're actually at very low boosts. I think 6 pounds a boost in their factory configuration. But yes, really big solid motors where they have a cast iron block, fairly conventional 2-bolt main system. Compared to what was previous, if you compare the FJ20 series engine to those Z18s that were in, say, that little white Bluebird that I talked about, that, in the end, that white Bluebird had pole position at Bathurst in 1984 in Australia, and that's a lap record that remains today because they changed the format of the track. But those little engines only had little M10 head studs. Cylinder clamping's an issue. You compare them to the FJ20, the Nissan Motorsport department have learned a lot about how to get these engines to hold together in motorsport, and so they designed them with an M12 head bolt straight out of the factory. And a lot of those things are quite good for performance. They've just empirically learnt how to make the engine survive without necessarily knowing the finer points. So they're fit for the purpose at the time.
The head gasket sealing is something that comes up pretty regularly on this podcast. And I mean, it's always sort of the fuse, as I put it, for a high boost turbocharged engine. And really, you kind of the limiting factor, and this is my own experience with my 4G63 program, the limiting factor on how much boost and hence how much power we could ultimately end up making was whether you could keep the cylinder head attached, and it gets increasingly more difficult the more cylinder pressure you're ramming in there, correct?
So it's certainly good food for thought. Once you lift the cylinder head and pressurize it, you get the combustion gases into that coolant, you know all about it. And it's a critical part of the solution to going to these high horsepower levels, which is where we were aiming. I think a lot of the 1980s Formula One teams learnt about that. BMW did it best. They actually used I think a BMW 2002 factory road going block type arrangement and developed that into the first turbocharged world championship winning engine back, I think it was in 83. And in the end, they developed that engine to the point where it was allegedly making 1,000 horsepower per litre, 1,500 horsepower out of a 1.5 litre four-cylinder for up to a lap.
Yeah, for up to a lap is the key point there.
A proper qualifying engine, but again, probably with the range of combustion issues, because I do remember seeing them on TV trailing smoke more often than not, probably halfway through the lap. And now I know there'd be a hole in that piston. And so they were dealing with these issues back then. And just over time, these older engines, I guess a lot of people who've worked with the more modern engines may not necessarily see a lot of those issues because they have been engineered out by the OEMs.
It's probably quite good for the Formula One teams at the time that they didn't have the grid penalties associated with using too many engines, because they were really treated as a consumable back in that period. But, you know, irrespective, impressive what they could do even for a lap, because a lap is still a reasonable amount of time to hold one of those engines together with the boost levels and the power levels that they were producing. Let's sort of talk a little bit about the development path with that Gazelle. Well, let's keep this one brief because I do want to spend some time on the dragster that came next. But essentially, can you give us the sort of 30,000 foot view of the combination you ended up running in that Gazelle and what that led to in terms of ET and mile an hour?
Well, it's still a good sound basic system done well. We had a aftermarket link ECU that controlled the spark. We still ran the original distributor to get, I guess, the ignition timing and for the ECU to know where the crankshaft was. So that was through a distributor drive, no crank triggers or anything like that. Ran 2 injectors per cylinder. I actually just put an extra lot of 4 injectors immediately under the original 2, pointing basically into the port. And we had a bigger throttle body, and we had a GT35R turbo and a decent intercooler. That was the one thing I remember. And you fabricated a lot of that pipe work, so you probably remember as well.
Taking me back a long way now.
But that's all that was.
So reasonably basic combination. There's no magic going in here, no sort of super exotic parts, just off-the-shelf basics and a very basic engine combination.
Well, we did obviously change. We had forged pistons and a set of Carrillo connecting rods. Factory block, factory crank, factory head, mild camshafts, around about 220 degrees duration, I think. That was my first FJ20 where I actually changed the camshafts. That was probably one of the bigger things, to try and free them up as opposed to having just the stock camshafts. RB20 Nissan 5-speed gearbox, so slight upgrade to the factory gearbox. Thicker tail shaft with a loop, because you don't want to have one of them break and sort of thrash around under the car. Just a steel tail shaft and just the factory R200 Nissan rear end. That's all that car was. Up to, at the start, it ran in New Zealand. We're talking early 2000s now. We ran as quick as 990, about 140 miles an hour probably. Before we moved it back, you would break various things in the drivetrain. I ended up going to a lovely carbon tail shaft to try and reduce some of the shock loading on the gearbox. The output shafts of the gearboxes were all, RB20 was the smaller original Nissan output shaft size. So we changed, after sawing off a couple of them, we went to an RB25 gearbox. It still managed to, that was the good thing about the Gazelle, the S12 platform, is you actually had quite a bit of room in the transmission tunnel to put the larger factory 5-speed gearbox in there. I think we ran Z31 300ZX drive shafts. Remember, and you probably remember this back in the day, is my budget was $100 a week. That's all I would be. I'm a hobby builder. building these cars. $5,000 a year is all I would spend on them. Probably to your frustration as the local speed shop.
Little bit. But I mean, it is important to also point out that you don't have to be spending tens of thousands of dollars to build something like this. And I mean, it was for its time a fast and relatively reliable car that could go laps and race competitively. And again, as you say, $100 a week budget, it's not out of reach of a lot of enthusiasts to build something similar.
No, as long as you're doing all the work yourself, and that's the other side of things, having that background with my uncles, but also just reading lots of books. And the internet wasn't a big thing back then. The internet was the information highway, but also the misinformation highway.
Definitely. I mean, nothing's changed there, unfortunately.
Well, it's probably even worse now, which is why HP Academy is so important, because you guys are the filters, aren't you?
Yeah, I that was really one of the things we were trying to fix with High Performance Academy. Part of it was we started with tuning courses, and realistically it was a case of creating the information that I wish I'd had easy access to when I was learning to tune, rather than having to figure it all out as I go. Obviously, we've branched into other topics, but having run a performance workshop for 13 years, I really got sick of the lack of information out there in the industry. Obviously, not all tuning shops or workshops are created equal. Unfortunately, the majority, I would say, and I think this is probably still a fair comment, don't know what they're doing. And the results that people get, unfortunately, for their hard-earned money, represent this. You're seeing cars that would come to us to be retuned, and they drive horribly, not make the sort of power that they should be making. And then, of course, there's always the horror stories about engines that are needlessly blown up by incompetent tuners. I mean, we were just trying to fix this and show that the whole industry, there's no magic here. These are just basic principles that if you understand, you can apply, and the average home enthusiast can do all of these things themselves if they've got a bit of patience and an eye for detail. And I mean, I think obviously you didn't learn through our courses, but I think you're a walking example of this aspect, really.
Well, it's about guessing less, isn't it, I think, and learning more. I didn't have the money to buy all the latest, greatest parts, but I could afford to buy a book, which may save me money, thousands of dollars, by avoiding an engine blow up. And of course, during all this time, I never hurt one engine during the development of this Gazelle. We eventually got that Gazelle down to 9.1. This is a full-bodied car, 9.1, 154 miles an hour through a 5-speed stick shift, independent rear end, and it would pull wheel stands. It needed
it's no joke.
It needed a parachute to be allowed to turn up at the racetrack. This is a car that was bought for $3,000. It never owed me more than $12,000, and we had a great time with it. But you get to a certain level of development with these things. I still remember we had boost per gear, all these fancy things. I had 3 micro switches on the gear stick.
That's one way of achieving boost per gear.
Yeah, and you'd have to continually adjust those things so that the gear stick would actually hit them, so you could actually, it knew that it was in second, third and fourth gear. And we used one of your twin plate quartermaster clutch with the slipper thing that we developed. You had one, we developed one as well, so we could let that clutch out just a little bit slower.
Let's just talk about that element for a moment, because I think it is worth dwelling on. Back when I was drag racing my Evo, and I think this is probably more important for the Evo platform, given it was four-wheel drive with essentially 3 solid welded up diffs, and it was a hair trigger thing to get off the line. I mean, it would either bog or potentially break something, or you'd light up all 4 wheels and essentially go nowhere. And I remember at the time sort of being hugely frustrated with this performance. And I was also involved with a team that were running a proper drag racing clutch, which is a slipper or a slider clutch, where they have centrifugal weights, and basically you can set the base pressure and the weights on the clutch to force it to slip off the line, and then as the RPM comes up and the centrifugal weight comes in, it would clamp, and you could really adjust how the clutch would slip. So basically it would allow the car to come off the line without bogging in, only applying enough torque to the tires essentially just to sort of create that light wheel spin without sort of buzzing them up to the limiter, and then as the RPM climbed it would lock up. So that was kind of the holy grail. Couldn't engineer one of those into a 4G63 gearbox, and I looked at the next best thing, which was, well, why don't we look at hydraulically forcing the clutch to slip? And I think back now there's a variety of off-the-shelf products available. Magnus Motorsport probably make the best known one, but back then either no one was doing it or definitely no one was talking about it. And I had a Turbo Smart pneumatic boost tee, the old school kind of boost control valve, which had a needle in a seat, so it had nice fine control. I looked at that and thought, well, hey, if I drill these out and tap it for some 8th MPT dash 4 fittings, I can kind of just plumb this into the clutch line, and then I've got this little dial. I can adjust the needle and seat, tweak that, played around with that, and I mean that was the absolute key to getting the performance out of my Evo. It kind of went from occasionally 1 in 10 runs running a half decent pass or braking in between to actually being, I'd say, reasonably consistent and going 180 mile an hour. Of course, the downside with it was it's very difficult with that arrangement, because when you've got it dialed in, if you put the clutch all the way to the floor and then literally just sidestep it, it'd probably take about 2 seconds, maybe 2.5 seconds to come all the way up. So it does make it quite difficult to cut a good light. But of course, back in the day, we were less interested in whether we beat the guy or girl in the other lane, and much more interested in running PBs, which really isn't drag racing, but I digress. That was kind of what we were doing. So yeah, again, you developed your own variant of that, correct?
Well, I was looking at what you had to go through, and that put me off racing a four-wheel drive car, manual car, for a long time. But essentially, similar thing. You can do various things to get these things to launch. That Gazelle used to run 1.332 to
That's
60
no joke.
foot.
Yep,
that's no joke.
Getting it done.
Part of that was actually launching it at 8,500 RPM. I used to have a launch switch that was enacted. It was just on the dashboard, and you could flick the switch and it would enable a 7,000 RPM launch in the first gear. But while I was adjusting that clutch thing, similar sort of setup to what you had, I would adjust mine so I could pull a light, but I had to hold a little button on the gear knob to energize a solenoid. To get this thing to work, you need a solenoid to divert the fluid through the clutch valve, I guess.
Important to note here, you're running a synchro mesh box, so you weren't clutchless shifting, were you? You're still using the clutch for the first, second, third, and third, fourth shift. So you've got to get that valve out of the system once you're actually off the line. Otherwise, it's going to artificially just slip the clutch through each of your next gear changes, making the car undrivable.
Well, you could develop, by then the ECUs could allow you to do a flat shift, but whenever I did that, it would break the synchro, the fourth synchro in the box. So even at this stage, the RB25 gearbox is good for 6 passes, 6 full power passes.
Consumables.
We've got over 700 wheel horsepower in this car with the little GT35R, but I was adjusting that clutch switch and accidentally, with my shoulder, turned off the staging limiter switch. And so the next pass, up till then we're doing 145s to 60 foot. The next pass, it runs straight to the 8,500 limit instead of the...
So you're just literally launching it off the engine rev limiter as opposed to a two-step.
Launch it off the engine rev limiter, and it immediately went 133. So it just liked being punished.
Nice.
So, which makes me think this Gazelle with the independent rear end, it's not a big dollar item. Like, to get it launching with the wheels in the air on the bump stops. So the way I actually made sure it launched straight was I'd take the springs out at home and do the wheel alignment based on the bump stops, and just adjust them with little donuts of rubber so that I had the same camber on both sides. But, there you go. It did what it did, and it's still actually the world's fastest, I'm told, for that platform. And I had a bloke the other day tell me he's coming after it with an S12, but it's got a 9-inch rear end and an SR20 VE. So
it's not the same.
I don't think it's the same. But anyway, that was the Gazelle. But at the end of the day, at that level of tune in a street car, there's risks involved with driveline failure. I always used to just shim the differentials, the limited slip differential, which was a clutch pack type, so that in the case if I broke an axle, and it never broke an axle with the carbon tail shaft. But that only lasted, that was some U-Butte thing that American ACPT in America made up. And I said I wanted a 3.5-inch carbon shaft. And they said, oh no, for your car, we do pro stock stuff. Your car will be fine for a 3-inch shaft. Well, it was, and it never broke anything for 20 passes. And then it broke the tail shaft into 3 pieces.
Yeah, I do find back in that era, I think there was from a lot of the shops, there was a bit of a disbelief, and you'd tell them what you were making, and they'd sort of look at what you told them and then decide that you were full of shit, and then give you what they thought you needed. And I mean, that probably was a pretty smart approach for 85% of people, but when you actually come across someone the likes of yourself or me, you're like, no, I'm actually telling you what we're really making. This isn't hopes and dreams, and I kind of know what I need. I faced that a few times. I just a little anecdote before we move on from this, just to come back to the clutch slipper, because this is something I don't actually know if I've ever told anyone this before, but I ended up with the most bizarre staging approach with that Evo. So we had this clutch slipper, and what I really wanted to do so we could cut a light is you kind of wanted to preload the clutch so it was just starting to take up before you'd come up onto the two-step. Otherwise, there was sort of this dead spot, and it might only be a tenth of a second, probably much less, when you first sidestep the clutch before the clutch would actually start to take up. And obviously that affects, first of all, your RPM, where you're actually going to leave the line. You want to get that consistent. Secondly, there's going to be that time delay, making it impossible to get a good light. So what I'd do, I actually ended up putting a line lock on the clutch as well. So I had that on the steering wheel. So what I'd do is I'd come into the first light, and I'd get that clutch to the point where it's just taking up, and then I'd creep it into the second light and I'd hold down that line lock. So at this point I've got a little bit of preload on that clutch. The problem is if I just went straight to full throttle, brought it up onto the two-step, the increased RPM, the car would creep through the light. So what I'd do there with the line lock, no longer needed my foot on the clutch, so I'd actually put my left foot onto the brake pedal and I'd hold the brake. We could have done this with a staging handbrake, but I didn't have one. And then I'd go to full throttle. So then the actual launch procedure, when the light would come down, I'd have to let go of the brake and get my finger off this button on the steering wheel at the same time, and then everything would sort of work. It was the most bizarre thing to launch, but I mean, it kind of got the job done anyway. You do what you need to do at some point.
Well, yeah, all these toys are available nowadays. But to the credit, back to my tail shaft, it was in 3 pieces, yet they said, oh, you'll have to send it back to us for analysis. So I just sent them a photo and said, well, I think if we'd made the shaft that I'd originally specified, we may not be in this situation. And to their credit, they actually built the 3.5-inch carbon shaft and sent it back over, because I guess their pride was wounded a little bit by this little Nissan 4-banger. But by then I'd decided there's driveline breakages are going to end up in the wall. Let's go find something. We're still not at the limit of these engines, 30 pounds of boost or a bit over that, or probably nearly 40 at that stage. I'd switched to methanol, and we wanted to see how far we could go with this FJ20 platform, which is where the dragster came in.
Okay. Before we move on to the dragster, I just want to comment just something you said about the limited slip diff in the back. And I mean, quite often it would be typical for a pure dedicated drag application to run a spool or solid differential with, obviously we don't turn corners, so we don't need that differential action. And then the spool or a welded center means that you've got even torque being distributed to both wheels. And that's great until it isn't. And when it isn't is when you break one half shaft. And I did actually mention just before that with my Evo we had 3 welded diffs, and that's actually not quite true. We had a welded centered diff, we had a welded front diff, but I actually purposely kept the limited slip in the rear and just shimmed it much tighter than stock. And the reason I did that is exactly what you mentioned there. Very common to break a rear axle in that car, and if you did that with a welded rear diff, you'd be straight into the wall before you knew what had happened. So if the case with the LSD, all it would do was basically open up the LSD and feed all the drive to the broken shaft, and you just go nowhere in a hurry, but at least it was nice and safe. I just thought that's information that probably a lot of people wouldn't think about. So sometimes you've got to put safety in favour of maybe outright performance. I mean, ultimately the LSD, with all of that torque being put through it, it's probably going to be locked up 50-50 anyway. So there's probably almost no downsides to it, I don't think, maybe other than a little bit more complexity.
Well, definitely from my point of view, it had a LSD in it, and a spool would cost me money, which I didn't have.
Oh, there you go.
But
some MIG wire doesn't cost a lot.
Oh, yeah, but remember this car? I used to drive it on the street and out at the racetrack. So it was a dual purpose thing. And as it turned out, it used to, until we upgraded the stub axles, it would break them. And that's something I learned from that. If you shim the diff up, it can act for all intents and purposes and do what you want when everything's going well. But if you break a half shaft or a stub axle and it doesn't turn you in the wall, it actually will overdrive the discs in the LSD and you stay straight. And
only downside really there is you sort of find yourself having to pull the diff apart and shim it back up to get the preload back to where it was, because putting all of that through a diff with a broken axle doesn't take too long to loosen up, unfortunately. But definitely the lesser of two evils. I'll take that any day over other than sticking the car into a wall. All right, so let's move forward and talk about the dragster. So you're back to Australia at this point. You've got the Gazelle down to 9.1 at 700 horsepower or thereabouts, and you wanted to actually see what this FJ20 could do in a chassis that was more designed around putting all of the power to the ground. So you partnered here with your uncle Jeff Watson on this project, and what sort of came of this?
Well, we actually at the time did stop and have a look. Jeff had finished racing his Sprite by then. He actually had an accident in the top end, and it's probably something we should probably reiterate to listeners here. Safety has always been one of my priorities, like the highest priority for a lot of these things. I had two young kids by then. You don't have a lot of money to fix broken cars or wreck engines. And so for me, it's been avoidance. It's been identifying the potential issues and addressing them before they happen. That's how you manage to have a car like the Gazelle and then sell it for probably more than I bought it for to the next person, instead of having it like in a big heap and take it to the tip. So that's essentially what we were trying to do with the dragster. Jeff had, after his Sprite, he'd spent many, many years tuning a variety of cars, including top bikes on nitromethane and also top alcohol cars into several Australian championships. So for Jeff, I guess it was a bit of a chance to maybe, again, explore the limits of the FJ20. But at the same time, we did look at the other engine platforms that were available. You were working with the 4G63. The GM Ecotech program was going on at that time. And we did have a look around at these other platforms. And in hindsight, we would be going faster with either of those two platforms. But at the time, and we're talking 2006, 2007 here, it wasn't exactly clear what the limitations would be of these earlier platforms like the FJ20.
So essentially you didn't know what you didn't know at that point.
Well, you don't know what you don't know when you start to push the limits. And the other thing is, when I priced up the price for a full GM Ecotech, so we're looking for 1,000 horsepower. You priced up a GM Ecotech that level, it was 30,000 or 35,000 US. An FJ20, I could still get it for $500 or $600 as a base engine. It's not the case anymore, but it was back then. And we already had quite a lot of, I suppose, tuning knowledge, to be fair, for those engines. So we thought, well, let's stick with it and just see how far it can go.
Yep, yeah, that's fair enough. And to be clear, for those who haven't ever heard of it, the GM Ecotech engine, which we might dive into in a little bit more detail shortly, that was essentially an import drag platform developed with the might and backing of General Motors, which is pretty rare realistically, isn't it?
Yeah, well, it's actually, they brought out a build book and a whole range of other information that we did get our hands on to read. And this was, I guess, the noughties, the year 2000s equivalent to those old How to Race Your Datsun books from the 1970s. So GM were very serious with the sport compact racing. I remember at this stage, Fast and Furious had, I guess, mainstreamed this racing of these small capacity, high boost engines.
Probably the time, maybe off the back of that sort of Fast and Furious as well. I mean, certainly here in New Zealand, but I saw it happening in the US as well. That was when the sport compact drag racing was at its prime. And it's definitely dropped away in terms of popularity now. I think a variety of reasons. Drifting has sort of come and overtaken it as a spectator sport, probably. It's got the OE backing as well. There's a lot of money in drifting. And I think also it got to a point where you sort of went, when I started drag racing, you could be pretty competitive in some of the classes with a home-built car, and you didn't have to be sort of pouring hundreds of thousands of dollars into it. I mean, you mentioned with your Gazelle, $5,000 a year was your budget. And over time, it got to a point where you would need to be spending hundreds of thousands of dollars if you wanted to have a chance of winning. And obviously that just takes it out of the realm of what's realistic for most enthusiasts, I think.
Yeah, well, the average person. But back in early 2000s, there were world records to be had. 6-second zone was a new thing. It had been beaten for a 4-cylinder car. We're talking about here in the States. They had gone that fast, but not anywhere else. So in the whole southern hemisphere, you could be the first into the sixes, and that was actually one of the things we wanted to do at the time. And so we were chasing that.
All right. So let's talk about the learning curve with this FJ20 once you had a platform and presumably a turbo that would allow you to start exploring the outer limit of what the FJ20 architecture was actually capable of. Where did you start seeing the limiting factors, and what were they?
Well, we talked before about you don't know what you don't know. Well, didn't we learn a lot? So you can take a tune-up from one platform, like an FJ20 in a factory car where it's factory located on factory engine mounts, a range of other things, use the factory distributor. And then we decided for this dragster, we can make as much power as we want. It has 40 spline Mark Williams axles, full floating rear end. There's wings, there's downforce. So we would build up an FJ20 to take advantage of those things. We got a billet crank made so that we could adapt it to the chassis, the dragster platform Jeff bought the car to make sure again that we were safe. He bought quite a good car. It had a 555 cube rare Morrison big block in it, and I got to drive that a couple of times, which was a bit of an eye-opener, just the immense amount of torque, and it ran into the 760s quite easily with that thing, with the automatic transmission. So all of that was available, so we adapted the FJ to the automatic. Turbos with the automatic, completely different thing. Jeff had a fair bit of experience, so with his Sprite, which also ran an automatic. We built the engine with the bigger cams, same Carrillo connecting rods, different pistons. For the turbos, with the auto, building boost to get them on the converter, it's really quite difficult. So we actually upped the compression ratio.
It's always an interesting conversation around compression ratios for turbo drag engines, particularly when you're running on a really good quality fuel such as methanol. You can get away with some compression ratios and boost pressure that obviously you'd never even consider on a pump gasoline. You'd just be knock limited straight away. So interesting to hear where you ended up in terms of compression ratio and what the sort of balancing act or compromises are with choosing that compression ratio. I'm guessing what you're getting to here is you're trying to optimize the torque the engine's producing on little to no boost, so you can actually get that thing up on the converter so it can start to spool the turbo.
Yeah, absolutely. So the Gazelle's 7.7, 7.8 to 1 compression, which is basically a factory Nissan compression ratio. We wanted to up that around the 9s or the low 9s just to try and improve the bottom end torque, but that involved a flat top piston. We'll get into that a bit later. A range of other things. The other things we did was we converted to a crank trigger instead of relying on the distributor to tell the ECU where the crankshaft was.
And the benefit, at least with the FJ20 compared to the later crop of Nissans, which have got very, very well-known issues surrounding their optical trigger cam angle sensor, and that just becomes completely untenable once you start working at higher RPM, and particularly with larger cams and heavy-duty valve springs. The harmonics just play havoc with that trigger, and essentially, you're ultimately inferring the engine position or the crankshaft position from the cam, which is never really going to be a great move in the first place. So obviously switching to a crank trigger where you're directly measuring the engine RPM directly from the crankshaft makes a lot of sense, right?
Yeah, well, we didn't know how much the factory FJ20 runs it basically off the cam drive, off a jack shaft halfway up the cam drive. And as it turns out, that does retard the ignition timing quite a bit and subject it to the torsionals and the other harmonics that are in that valve train. But back at that time, we didn't know how much that was an issue. But we did choose, we were well aware that FJ20 runs the same optical thing. It was probably the original one that led to the problems that you'd see with the SRs and later on. So we would change them from a 360-degree chopper wheel to a 4-in-1. So it only had four. It knew that TDCs basically, well, that's it's running at half engine speed. So that was about all we could use with the Gazelle, but that's what we ran, and it worked quite well. The ECUs could infer from that. But as it turns out, what we'd have in our ignition map and what actually the engine gets at 6,000 or 7,000 RPM are actually two different things. Very different things, which we found out a bit later.
And I think that's really something that any tuner should be keeping in mind. I drill this into people about the importance of setting the base ignition timing, because when you're looking at that laptop and you've got a number on the screen that says your timing is X, 20 degrees, for example, it's human nature just to blatantly, blindly believe that number and take it as gospel. And that, as you mentioned, it's not always going to be the case. And I think then the other element there, which is easy to overlook, is that the timing that you're getting at idle when you set your base ignition timing, that's not necessarily still going to be where you're at when you're at 8,000 RPM and the like, and everything's moving around. And yeah, it can be an eye-opener what's actually happening if you happen to be brave enough to take a timing light and actually run the thing at 7,000 RPM on the dyno and see what your timing's actually doing.
Yes, but for a lot of us who also work with the older distributors, points distributors and such, like in the early L series, we are used to seeing retard. So we had a rough idea that might be happening. When you talk about later ECUs, and the other things we changed was into a new ECU by we're actually getting our ECU sponsored at the time. Some of these ECUs have the ability to advance that without you knowing, through things like ignition delay and things like that, things that we weren't aware of at the time. And so it's fine if they're retarded from where you think they are, but if they're advanced from where you think they are, that's a whole different ballgame, and that was a lesson for us still.
It's a much more dangerous situation.
It was a lesson for us still to learn. So we also looked at, I was using factory inlet manifolds and things like that in the Gazelle, so we actually changed to cater for a bigger airflow, larger throttle body, and a different fabricated plenum. Jeff did all that work. He did a fantastic fabrication job. We had other people who wanted to provide us with a turbocharger and an exhaust manifold, and we let them do that. And we fabricated this whole thing together. Got it up and running through essentially the Gazelle's old tune-up in the thing. I mean, it wouldn't build boost. It just wouldn't run. It had the same primary injector positioning, but the secondary injectors were in different positions to the old factory manifold, where I'd stuck them basically on the bottom of the port pointing up. These ones were outboard in the runner. And we found out very on this car and this, it's the same engine, it's a different ECU, different injector positionings, slightly different camshafts, bigger turbo, doesn't want to build boost. First issue was the turbocharger. Eventually we found the car was extremely lean. It wouldn't build boost. It was acting, it would backfire. And we're thinking we've got an ignition misfire, but reading the plugs. So we're back down. We have Lambda. We have all these other things. We have EGTs. Looks like it should have the fuel. I would run the Gazelle in the Lambda around the mid-70s, Lambda 0.7, 7.5. A bit fatter than some people run them, but we'd never hurt an engine running in that way and made good power.
So you've still got the Lambda sensor on this new dragster build. So the numbers that you're seeing here, so I'm just interested to dive into this. I think there's an expectation these days that the art of reading plugs is irrelevant. It's gone by the by. It's old school technology. We've got a Lambda sensor now, so that's all we need to do is check our logs. So you're saying that the Lambda was reading where you expected, but when you look at the plugs, they're visibly showing that they're lean?
Exactly. And in fact, it's so lean that the car, because when you have a torque converter, you can put the trans brake on, which locks the gearbox into first gear and reverse, and allows you to build boost. And to get a dragster or any automatic car down the track, you have to build boost or else it's going to leave it idle. This thing wouldn't build boost at Lambda 0.7, wouldn't even build boost at Lambda 0.6. And where they're going, well, this is crazy. So you start not trusting your data.
Yeah, it would be confusing.
And in the end, we got this thing working by reading the plugs. and added more and more fuel until it would actually run up. First time it actually ran up, and then it shat the turbo that was provided by us by the sponsor.
That's not helpful.
The U-boot ball bearing turbo. So then we went and bought a Borg Warner, and then we actually Borg Warner 76mm and started from there, and actually got this thing to build boost on our little dyno. We don't know what the horsepower figures are, but we know whether it's working or not. We thought we had ignition misfires, but we actually didn't. It was actually just too lean. And eventually we got it to the stage where we could take it to the track for the first time. And so we build boost, stage the car. I'm running this thing. We run, it goes to half track. Well, you have to actually license the car. So we did some half track passes and sort of sorted the thing out and thought we had it doing well. But the first time we took it out for a full track pass, did a fantastic burnout. Singing there at 9.5, 10,000 RPM in top gear, which makes a very spectacular sort of view. You run the thing to half track and it throws the rods out.
Ah.
Right. So it actually, first time I've ever hurt an engine.
Okay. Well, that's not one of the firsts that you'd ever aim for, but yeah, well, what did you learn from that failure?
Well, first of all, you can crush Carrillo connecting rods, the H-beam rods, when you the cylinder pressures get too high when you go through an abnormal combustion process. They crush. When the rod shortens to a point where the counterweights of the crankshaft start machining away at the bottom of your piston, it gets to the stage where the piston pin is freed up, and then the rod becomes free. The pistons end up in the combustion chamber, the piston top. The pins are in the nappy, and the rest of the rods proceed to lathe the engine apart so you can see through the blocks. So that happened in number 1. Number 4, still remember it, couldn't believe it. And we had to sit back down and have a look at this thing and say, well, what's it actually really want? And as it turned out, the new ECUs have a whole range of different settings in them that we were getting these ECUs before they, from the sponsor, before they actually provided all the documentation. And there was this setting called ignition delay.
Okay.
So ignition delay, actually didn't know what that was. But to set up the base timing, we actually used a timing map that was provided by them, which from an SR20, and then put our numbers in it because we knew where our fuel basically was and our timing. But ignition delay, as it turns out, and we found this out probably several months later, we're building the next engine. Actually, we rewired the whole car and did a whole range of other things as well, thinking that we had misfire problems or a range of other things. But ignition delay, when you have a crank trigger, there's very little delay. Ignition delay is something that the ECU manufacturers have put in to compensate for that ignition lag in timing with RPM. But when you don't have ignition lag with a crank trigger, and if you have an ignition delay setting in there that was put in, that was in the base map that we didn't know about, when we eventually found this out, we ran the timing light on this car. We were aiming for a bit under 20 degrees of timing, 40 pounds of boost. We just started at the same boost we had the Gazelle. But by the time you're at 8 or 9,000 RPM and it shows 40 degrees of time instead of 20.
Oh, that's quite optimistic.
What you're doing is a sweep, aren't you? Doing a timing sweep when you run down the track. So that's how we wasted our first engine, is not understanding or asking about a new ECU feature that we didn't know about.
Yeah, that's frustrating. And that feature, the ignition delays, are pretty standard now across the board on most mainstream aftermarket standalones. And, so the principle is you set your base timing with the timing fixed at idle or just off idle, and then you bring the RPM up to maybe 6,000 RPM and check, and basically you can adjust your ignition delay so that the timing stays flat right the way through the rev range. But yeah, of course, if you aren't aware that system's there and you don't have the delay that's expected, it's artificially going to advance the timing, which is obviously the last thing you want to do. So I assume from that you ended up essentially running the engine into detonation, and that caused the spike in cylinder pressure and the resulting damage.
Well, we think that's probably what happened. It was telling us something by the cylinders that went first, but it basically did a sweep till it met an abnormal combustion condition. But what we found with those connecting rods, the H-section connecting rods, the Carrillos, were good for about 1,000 horsepower. Even then, in the GM Ecotech program we were corresponding with those guys, and they actually had to move away into an I-beam sort of set up out of 300M because they had rod buckling issues. So we looked at the con rods as well and actually got Manly to design us a 300M I-beam rod, which, it just doesn't buckle at those power levels.
Pretty common with dedicated drag engines to go to an alloy rod. Admittedly, pros and cons with the alloy rod, but they do, for the most part, seem pretty well suited to a drag application because the fatigue life is less of a concern. Interested to hear why you went 300M instead of aluminium.
In the short term, we were only shooting for 1,000 horsepower. The steel rod should be well capable of those type of things. Also, from a service point of view, we're not once we get things running, we're not really keen to pull them down that often. So and we knew that the steel rods should be capable for what we were after. So that was, everything's custom for an FJ20 at this sort of horsepower level from our point of view. And also, the minimum run for those rods was 40 rods. This is a custom engine. No one builds these things for FJ20.
It is the downside of dealing with something that isn't mainstream popular. And I mean, I'd say the same was probably true when we were developing the 4G63 back in the day. I mean, obviously that's a popular engine, and these days you can buy any component you want from hundreds of manufacturers off the shelf. But back then the popularity wasn't there, and the support and the aftermarket wasn't there, and it was incredibly frustrating getting custom rods made and the lead times for all of those parts. It's definitely easier if you're dealing with the mainstream engines, for sure.
Yeah, so I don't know whether it's false economy dealing with the cheaper engine at the start, but we could keep that cost down by getting a 40 run set done, keep 2 sets for ourselves, and then group buy 8 away to other people who really appreciated the steel rods that essentially designed for 300 to 350 horsepower, 400 horsepower per cylinder, nearly capable. Not too many people in FJ20 land wanting to use an alloy rod, but there were plenty of street racing and circuit racing guys who could use the steel rod. So that's actually the way we went.
Let's just come back to the failure. And unfortunately, particularly drag racing, where you're trying to beat world records or be the fastest, this is the area where I would say that failures are unfortunately going to happen if you want to push the boundaries. And that's very different to the usual information I give. And there is a misconception, I believe, out there that if you want to learn how to tune engines, that you have to break engines. And I absolutely disagree with that in a street application or even a fairly heavily modified road race application. Applying good principles of tuning, understanding knock, listening for that, and avoiding it. I believe that there is no reason why you should be breaking engines. But when you are starting to push those boundaries in drag racing, that's the point you're going to get to. And really the key with any of these failures is, obviously it always hurts and it's definitely going to hurt the wallet. But I think the important part is being able to learn from the failure rather than ignoring the evidence. And sometimes that evidence is really hard to kind of learn from, because these failures, if they happen at 9,000, 10,000 RPM, often there's not a lot left. But the danger is basically reassembling the engine and going again and suffering the same expensive failure. So what did you learn from analysing what was left of that engine that guided you in the direction of what was actually going on?
Well, first of all, you learn that the engine nappies they catch most of the shrapnel, and it looked like a war zone down there. I've still got some of the pieces. I have my wall of sacrifices to the gods of speed here, and they're really good conversation pieces. But from the point of view of that, remember at this stage, we're just trying to replicate the same boost pressure as the Gazelle had. Right? So what we're learning here is it's a different chassis. We have a solid mounted engine, that comes into it a bit later. It's a completely different environment. So what we were using, the tune-up that we had in the road car just wasn't working. Looked completely different, and all of these different variables that you don't immediately think of actually do affect how things operate. So we put together another engine, salvage what we could. I think the crankshaft and the bottom girdle. We fabricated a girdle for these engines to try and help the 2-bolt main caps survive. The other things we were finding from those early passes is the torsional vibration. We'd never seen problems like that in the road car, but trying to get, say, the front pulley off this engine or the flywheel off this engine after it had been run at that higher power level, they were trying to weld themselves onto the crankshaft. So all these different things based on the fact that I think we've got a solid mounted engine now with the bottom end we've stiffened up with the girdle, and there's these inherent design issues related to torsional vibrations and harmonics in these engines in the drivetrain.
So just things that you would never see in a road application with everything rubber mounted.
No, they start appearing. And you know about them because it looks like a dog's been chewing on the part.
Yeah, never pleasant.
So we had to add more bolts to the flywheel. We're running quite a thick flex plate to try and hold the flywheel on. And eventually we actually ended up going to a second crankshaft, which had, originally we had 6 bolts and 6 dowels, which is what Crowler told us, this is the gun thing to use. But we're reading the Ecotech handbook where they actually were using 12 M12 bolts trying to hold the flywheels on these things. And in the end, we compromised and ended up with 10. We could fit 10 bolts at the PCD that we had to try and hold that flywheel on.
I assume that required another custom crankshaft to get that rear flange.
Yeah, well, that's the second custom crankshaft. And then, well, the other thing you learn about the torsional vibration is just because you've bolted the crankshaft on, the flywheel on properly, doesn't mean it goes away. All it did is move it directly to the front of the crank and require us to develop, actually ended up with an ATI harmonic balancer to try and dampen some of these issues that we were seeing in that bottom end. So we're developing these engines essentially through trial and error and uncovering things that were inherent in that basic design that back in the 1980s, Nissan would never see.
Yeah. Because
they've never they probably rev them to those higher levels, but the specific horsepower, that cylinder pressure and that boost that exaggerates and magnifies all these issues, we were finding them as we went along.
Definitely. Let's fast forward the sort of development process. You did ultimately get on top of these problems. So let's talk about sort of where the dragster ended up in terms of power, ET and mile an hour.
When I just refreshed myself the other day and looked at one of the tables that I have on how we went, I suppose in steps and jumps, we got the car to the end where it would go down the track. It was a big improvement to something that throws the rods out halfway down. That Borg-Warner turbo, we got as quick as 7.4s, high 170 mile an hour, which was the quickest 4-cylinder car in the Southern Hemisphere at that time. So even though we're struggling with this thing, it's still quick relative to where things are at the time. And then looking at ways to improve our performance, Jeff went and invested in a GDX 4508 Garrett, and that dropped us more than 3/10 straight away.
Wow.
During this time, of course, we also had to learn things like how to get the thing up on boost. That no matter what we tried with the higher compression ratio, it needed NOS, a 50 shot of NOS, just to actually pull it up on the converter to get it going.
I haven't seen too many small capacity import engines do a good job of getting up on the converter without a small shot of nitrous. I mean, unfortunately, they just don't have the bottom end torque that's really required, correct? Particularly once you put a larger turbo on them.
In the end of this story, we can tell you that some of the Hondas definitely do, because we found that out in the end of this whole progress. So essentially bolting on that Garrett dropped us it ran 702.
Dangerously close to that 6-second bracket.
Dangerously close to the first 6-second pass in the Southern Hemisphere in this little car. The issue was it would still occasionally just hurt itself. We're talking about a pre-ignition combustion problem that's inherent in these engines after we ironed out a whole range of other issues. We set out to run this engine below lambda 0.5 to get it go down the track under boost.
Which is crazy rich.
Well, that's crazy rich if you're measuring by the lambda sensor. By then, Jeff had made sure due to all this top alcohol experience, we'd put a race pack on this thing. So we were having a really close look at the EGTs, actually tuning this engine like a top alcohol car and keeping the EGTs around 1,000 Fahrenheit, which is like on the edge for an alcohol car, which is 600C or 580, 600C, something along those lines. And so, it was essentially tuning this thing more like a top alcohol car than a sport compact thing was actually how it was going down the track. And I actually, looking back now, I put this down to various things, and it's a combustion chamber design that we could talk about a bit later, and also injector positioning and our inability to actually vaporize the amount of fuel that this engine needed to go down the track. So we can't talk to anyone. We can talk to, and we did talk to you about it. This engine's acting very differently to the other sport compact engines, and a lot of it does stem back.
Certainly we weren't seeing anything like this in the 4G63s, although, I mean, they weren't by any stretch of the imagination bulletproof at those sort of power levels, but it was responding very differently to anything that I was involved with.
Yeah, and I put that down actually now in hindsight to the actual port design as well as combustion chamber design, because the FJ20 has a round port, and again designed for carburetors originally, without the benefit of all the modern CFD and the other design factors that go into these engines. And so we're getting an exaggeration of some of the combustion problems and some abnormal and unstable combustion that ends up being, I think, the critical key to making really high specific horsepower level in these high boost piston engines. And so we didn't have stable combustion. The other thing we noticed was our fuel pressure, or we mentioned torsional vibration before. So once we actually put a damper on the front, we weren't chewing up. Oh, that's the other thing. So you forget, you pull those engines down in those earlier passes, you might do one pass and check in the sump, and all the rubber for the lower chain tensioner is in the sump. So it's eating up a chain tensioner in one pass.
In one pass, great.
And so we had to go develop a chain tensioner out of, these are chain tensioners which lasted 2, 3, 5 years. In the other cars would last one pass in this dragster.
And that again sort of comes back to the problem when you're treading that path that no one else is going down, is you can't learn from others. You're doing it the hard way, and you also don't have the ability to buy these parts that fail off the shelf. You have to develop everything yourself.
Well, first of all, they don't believe you, so you start doubting yourself. Well, we found some of the latest and greatest. It wasn't Teflon type stuff, but it was really decent quality, hard, machinable plastic that you can use for the timing chain tensioner material. And we put that in, and that made it live, that with the damper. We could actually make that part of the car live. But the vibration doesn't go away.
No.
And so when we're data logging a whole range of things, and a lot of really important stuff is fuel pressure. Oh, the other thing is there's no coolant in this engine by then. You can't keep coolant in them at this power level. We would run, the cylinder sealing went from an MLS head gasket in the Gazelle. We went to actually it's a spring energized C seal that we use, which is actually designed for nuclear reactors, because the peak cylinder pressure at this power level is 3,000 to 4,000 psi. That's nothing in a nuclear power reactor, apparently. And you can get these lovely Inconel seals that actually can move up and down with the cylinder heads, and that was working really well.
I do remember when you went down that path, and I mean, this sort of comes back to, there's so many different techniques and technologies that have sort of been developed over the years. I mean, back in the F1 turbo era, I believe, I mean, obviously there's scant details available, but they were using gas-filled O-rings, and then there was O-rings available which had little holes facing the combustion chamber, so they would actually fill with combustion pressure. And then the C-spring, a sort of similar thing. You could get that combustion pressure inside them and it will actually expand it out. Because obviously we look at these components, the block and the head, when they're sitting on the bench before you assemble them. And I mean, they're rock solid. But of course, with 3,000 or 4,000 psi of pressure, they're actually flexing around a bit like a noodle, aren't they?
Well, and that's the other thing that we were learning at that time. It was slowly dawning on me, is this combustion chamber designed for rally, with the big squish areas on the sides of the chamber. What are we doing there at 10,000 RPM and, 45, 50 pounds of boost now? Are we getting stable combustion, or are we getting quite harsh combustion through this process? And so the FJ20s are renowned for lifting the heads at quite relatively low cylinder pressures. And when you look at them, they've got a big head stud, big M12 head stud, and a range of other features. But that combustion chamber design is designed for something else.
Sure. Well, we want to get deeper into sort of analysing what's going on inside the cylinder, the combustion process, and some of these forms of abnormal combustion. So I think it's probably a good time to segue towards that, and sort of we can talk more about how this relates to the FJ20 specifically. But before we sort of park this dragster, what did you ultimately get down to at this point? You sort of, I think you said 770 something. You did get it into the sixes before the project got parked?
Definitely the sixes were around 2013, flat top piston, 693 at 190. I think we just missed being the first into the sixes by a month or so. I think Colin Wilshire beat us there. We heard a piston again on that same meeting. And it's starting to see we're getting what looks like a bit like a random pre-ignition problem. And so we worked through various iterations, trying different piston designs. The best performance, we're measuring crankcase pressure as well as fuel pressure and all the usual things, EGTs. The one thing we're picking up is when the engine is run fat and we're sort of creeping up on the fuel. If we change something and we start running it rich, the fuel pressure is relatively stable, but as we start to tune this thing up and it gets quicker, we start to see these fluctuations in fuel pressure at quite a high frequency. In the rails, we're measuring directly out of the rails, and we tried everything to fix this problem, different diameter fuel rails, different fuel regulators, the big Weldon one we ended up being, everything, bigger bores, nothing could fix it. And then you start thinking, well, is this data good? Is this an interference problem? The dragsters have very little body in the dragster. But we see a lot of people who move supposedly quite well-functioning engines out of a sedan into a dragster and say, oh, we're going to run really fast, and they can't get the things to work with electronic interference and a range of other things. This wasn't that. This actually, as it turns out, is actually the fuel pressure in the rails is fluctuating quite markedly. We tried fuel dampers and a whole range of other things. And the other thing we would look at is the crankcase pressure, which told us essentially how much the blocks are flexing and how good your ring seal is. And that was really an interesting process, because when the engine's happy and running well, we ran down as quick as 683 in the end, 195 mile an hour. But it was doing that happiest with the least pressure in the pan with a set of dished pistons with the lowest compression ratio. And in the end, the fastest pass we actually ran was going to be, when we look at the data, by then we're 2015, I think 2016, we look at the data. This last pass that we ran, we had tried a bigger plenum, again, different fuel rail setups. This vibration's still there. The fuel pressure's still, it's a high frequency fluctuation. It was going to run a 670, something in the mid 670s. The ECU that we had, I remember we were trying to move away from closed loop boost, which is what we were using. We could see there was a bit of a drop after the launch. This car in the end was 60 footing in 1 second flat, 100s, half tracking really well and then sort of laying over near the top end, as opposed to, it should have been running nearer 200 miles an hour, but we could never quite get that top end sorted. And at 670s, this last pass, it was going to run that to 900 feet, and then we lost number 2 cylinder again to look like pre-ignition, and rolled through to a 683, I think 187. But all this time, whenever you, in these engines, and again, we hark back to that safety that I was talking to you about, once we have crankcase pressure, and we know when the engine's happy, 1 or 2 PSI in the crankcase, when we start to see a little bit of abnormal combustion, the crankcase pressure will increase to 15, 20 PSI in the sump. It's a wet sump.
So you straight away know that it's basically over. Are you using any safeties based on that?
No, well, we tried a range of things, but it all happens too quickly. If 20 PSI, the engine lives, but you've had abnormal combustion, what it's doing is flexing the bores. We ended up, our last engine actually had sleeves. These are completely filled engines. There's no coolant left in them. They're all concreted up. Still flexes the bore, and several blocks we actually, they wear out oval as they just get pushed out around by the thrust and the cylinder pressure. Billet blocks would be fantastic, but of course no one will ever build a billet block for an FJ20.
No, that'd be an expensive one-off.
But when, in these instances where you hurt a piston, the data that really made you stop and think, and in the end, we ended there in the 680s or high 670s sort of performance, is when you hold a piston and we look at the engine data, it occurs in less than 100 engine cycles at 9,500 RPM, 50 to 60 pounds of boost. That last run, we had to guess on our wastegate duty cycle because we were trying to go to open loop on the wastegate, but we actually didn't know that ECU didn't log wastegate duty cycle, and we actually just had a guess, thinking, oh, where are we? 55 pounds of boost in this engine. I said, well, let's try 50%. Again, I mentioned guess less. 50% duty cycle in our combination for that first pass. It just blew the tyres off this dragster. would not hook up.
Touch optimistic.
So we never fully loaded the engine in the first qualifier, and it ran through, I don't know, 720 or something like that with 3 stabs of the throttle, nearly put me in the wall. And we looked at the data, it was about 66 pounds of boost,
right,
which is 10 pounds more than what we had ever used before. So I said, we're not using that much in duty cycle in the wastegate, funny enough. So we dropped it to, I think it was low 40s. And the next pass was when it ran that, it would have been a 6.7, but we lost that piston at 900 feet, and it was 62 pounds or something a boost.
Not too bad for a 3-cylinder, at least over the back half of the track anyway.
Yeah, but the scary thing is when you hole a piston, which is pre-ignition, that's what happens. You end up burning a hole in the piston, and you look at the data for your crankcase pressure, and you have 8 litres of oil in that sump. It'll be 1 or 2 psi at the start of the pass, and then you start to get in the abnormal combustion, and it moves to about 20 psi till the piston goes through. And between the start of abnormal combustion and the piston going through, we worked out 100 engine cycles.
It's not a lot.
It's less than a second.
Yeah.
You're not going to get a warning light or any reaction, depending on how you set up your ECU, until after that piston runs through. So you have less than a second to get your foot off the throttle before you end up, I think we were logging at 50 hertz. When you looked at when the piston goes through and that combustion pressure can enter the sump, the pressure trace in the sump, it would go from 20 psi, and then the next one would be 50.
Yeah.
And then like 80, and then we've got a 120 psi sensor on the crankcase, and then it just bottoms it out. And you're saying, well, what's that? That's a bomb. I'm sitting on a bomb, traveling at nearly 200 miles an hour.
Yeah, doesn't bear thinking about, does it?
And it's trying to blow the sump off and 8 litres of oil under my tyres. And that's when we decided for the FJ20 platform that we'd seen enough, and that people want to chase our records, our world records.
Good on them.
They're more than welcome to go and do it.
Yeah. Yeah, and I think you do. I've found as I've gotten older that I have a newfound appreciation for safety, and you take it a lot more seriously, and things, when they go wrong at close to 200 mile an hour, you're going to be very lucky if you walk away from that. So I think that's probably a pretty sensible option. I just wanted to take a moment out of our interview with Ben and talk about a package of courses that I think you're really going to enjoy if you've enjoyed this podcast so far, and that is our engine building starter package. Now, I know for a lot of enthusiasts, they think that building their own engines is something they're going to have to leave to a professional workshop or an engine reconditioner. The reality is that nothing could be further from the truth, and actually our guest today, Ben, is a classic example of this. Without any professional training, he's building high quality race engines for some of the most expensive historic race cars in Australia. Our engine building starter package begins with our engine building fundamentals course, which, as its name implies, teaches you the fundamentals of engine building. You'll learn about the engine and how it operates, the parts inside the engine. You'll learn about the clearances and tolerances inside, and why we may need to adjust these clearances as we start building engines that make more power than stock and rev higher than stock. You'll also learn about the common machining processes that you'll need to have applied so that you're going to be able to speak the same language as your engine machine shop. From there, we move on to our practical engine building course, which will take your knowledge that next step further and teach you the steps involved in building your own high quality, reliable engine. Important to note, this course is generic. It doesn't matter if you're building a 4-cylinder turbo Nissan FJ20, maybe an LS3 with a blower on it, or a quad cam V12 with 2 turbos. It doesn't matter. The principles remain the same. We also include a simple 10-step process that you can apply to building any engine. By doing this, it breaks down the entire process into simple bite-sized steps that are relatively quick and easy to complete. In no time, you'll get to the end and you'll have a completely assembled engine, and you'll have the confidence when it comes time to start that engine that it's going to operate exactly as it should, delivering great power, great torque, and most importantly, great reliability. This course also includes a library of worked examples, which is an informal walkthrough of our 10-step process where you can see that process being applied on a variety of different engines to really expand your own knowledge. We're also including our How to Degree a Cam course, and this would probably be one of the most common upgrades that we make when we're building a performance engine. However, getting this wrong can mean at best you're not going to get the power and torque from that cam that the manufacturer intends. Worst case scenario, you could end up with an expensive failure due to piston to valve contact or valve to valve contact. This course teaches you how the valve train operates, how the cam operates, and again, we've got a simple step-by-step process that you can apply regardless if you're degreeing a cam in a pushrod V8 or a quad cam V12. There's also a library of worked examples so you can follow along and see exactly how it's done. You can use the coupon code Diggles100 and that'll get you $100 off the purchase of this engine building starter package. However, there's still absolutely no risk getting involved. We offer a 60-day no questions asked money back guarantee. So if you purchase and for any reason at all decide it wasn't quite what you expected, let us know. We'll give you a full refund of the purchase price. All right, let's get back to our interview now. All right, let's segue into what I was really interested in chatting about. We've kind of set the background here of your experience around this, but I think, as I mentioned, there's a bit of a lack of understanding about some of these forms of abnormal combustion, even though we've discussed them briefly on the podcast previously, but I just wanted to get a little bit more involved because I think out of the people I've spoken to so far, you probably got the most hands-on experience with seeing what this looks like when it goes wrong. In terms of the forms of abnormal combustion, we've got what most people would probably consider foremost as detonation or knock. And that absolutely is an issue. However, much more damaging and what we've been talking about off and on here is pre-ignition. So could you give us a quick refresher on the difference between those forms of abnormal combustion?
Well, in our experience of detonation, there's a bit of a kitten compared to pre-ignition. Our engine could survive through the noise. We had the knock sensor on the vehicle. The issue is at those specific power levels, you actually need to get sense out of a knock sensor. There's so much engine noise going on. And also, as we said, with these particular engines, there's harmonic vibration issues that we could never really get rid of as well that potentially led into some of these fueling or pre-ignition issues because your fuel pressure is actually joggling around quite a bit. 20, 30 psi variations at quite a high frequency in the rail. But the engine, you can pick up the detonation by some little divots on the tops of the pistons. We'd see that occasionally. The engine would survive that. You might pick up a little bit of increase in pan pressure through the run, but you look at it and go, well, it survived that, and you pull the engine down afterwards and not really see much evidence of the problem. We never damaged a bearing the whole time we ran these engines. They've got quite a big, strong bottom end on them.
Just to sort of elaborate on this, I mean, detonation occurs after the spark has actually initiated the combustion process, and ultimately we've got this expanding flame front coming out from the spark plug, and as that's occurring, we've got the pressure and the heat inside the combustion chamber continuing to increase. And that detonation is sort of occurring in the end gases around you, typically the outside of the combustion chamber. It gets to a point where the heat is so great that these pockets of unburned fuel and air will spontaneously combust. When they do this, they release all of their energy very, very rapidly, and you get these spikes in pressure. And I liken this to sort of someone slamming down on the crown of a piston with a sledgehammer, and it can be just as damaging as that sounds. So typical first signs of this, you'll sort of see a bit of a sandblasted appearance to the piston crown and sometimes the combustion chamber as well, and that's as a result of these pressure spikes essentially stripping away a boundary layer of gases that are protecting those aluminium components from the full heat of combustion. So that's detonation, and the key really with detonation or knock is it starts after the ignition event has initiated normal combustion.
Absolutely correct.
Pre-ignition, on the other hand, can you give us a bit of insight into that?
Yeah, well, again, I'll just top off on the detonation first.
Yeah, absolutely.
A great description of it. We can pick that up in our engine. As I said, the knock sensors are basically bottomed out by this specific horsepower level. We can see it in increased vibration in the fuel pressure side of things, but also pan pressure goes up. But your EGT, you can see the spikes in the EGT because, again, you're getting extra heat is being released quickly and into the exhaust stream. You can pick up some of those abnormal combustions via the EGT. So it looks different on the EGT, but we can pick it up.
So you've got a number of sources that you can actually refer this or validate this in the data.
Yeah, obviously when the engine's just behind my head as I'm running down the track, but you can't. Detonation was never so bad that you could hear the engine sort of run off song. You might pick it up in the ET. It might be 600ths or nearly up to 10th slower, depending on how early on in the run the detonation would occur. But you could sort of live with it at this power level because remember, there's no coolant. We've got a decent cylinder seal. We've got a 300M connecting rod that will not buckle. Even at those high cylinder pressures, we can keep the pressure in the cylinder, and the engine could live with it. Now, pre-ignition, on the other hand, it's ignition of that air-fuel charge before the spark plug's supposed to fire. The main issue that we found with that is extremely disruptive because essentially once you have one pre-ignition event, and again, I guess, of course, pre-ignition can be preceded by mild detonation in some instances if you're getting a heat release, and that can sort of increase your spark plug tip to the point where it exceeds its normal temperature and pre-ignites the fuel. But that's normally not what happened in our experience. In our experience, we were having other issues that were starting off the pre-ignition. But once you have one pre-ignition cycle, the likelihood of the next cycle being a pre-ignition cycle is that much higher because the engine's under significant load and you haven't got rid of the initial source of that pre-ignition. So once they start running into pre-ignition, it sort of feeds on itself. And if you can imagine the flame front, it's uncontrolled and it's occurring as that inlet valve's opening and you're injecting your fuel and air mixture into that environment. What is it? It is a blowtorch. That's what you're doing to that combustion chamber. What we were finding is, and you can trace the pre-ignition cycle and the flame direction of the pre-ignition by following the damage in the combustion chamber and onto the piston top. And I was looking at this, and essentially through this whole process, I guess I did my second PhD on practical combustion anomaly, trying to learn more about this thing because it's costing me money, it's endangering my life and requiring me to rebuild my engines.
Yeah, all good reasons to get on top of it pretty quickly.
Yeah.
Yeah, a key here is, just to be super clear, is with pre-ignition, the combustion is essentially initiated without the spark event occurring. And, there's a variety of reasons which you're going to get into, but essentially a hot surface can be sufficient to actually begin that combustion process occurring, and then it's sort of self-fulfilling after that, correct?
Well, that's the simplest form of pre-ignition. What was probably happening in our perspective, remember, we're running these things, we're damping out a lot of the simple detonation issues due to the fact we're running so much fuel in the chamber and quite a low EGT in comparison. We had to tune this thing more like a top alcohol car to get it to run down the track. Other things can happen to lower the ignition point of the fuel such that the spark, the hottest part of the chamber is usually the spark plug. But in our case, it's probably no chance that the spark plug was actually hot enough to initiate pre-ignition on its own based on the ignition temperature for methanol. And methanol as a fuel have great anti-knock properties of a very high latent heat of vaporization. The downside of alcohol fuels, and you're probably aware of this, but some people don't necessarily think of it from the point of view of when we're talking about the chemistry of that combustion process, because it's a chemical reaction what we're doing here. All those molecules are identical. So methanol compared to E85 is just another world away, because methanol, everything can be fine and you're making good horsepower up to the point when you're not.
Yeah, it's a very, very defined, very fine line, isn't it? You step over that and it goes badly very, very quickly.
And the reason because of that is because it is not a mixture of molecules. It is a monomolecular fuel. And so like E85 is 85% single molecule of ethanol, but it has 15% other things to, if and when you get into pre-ignition or detonation, they'll all go off at different temperatures and sort of cushion that blow a little bit.
So you don't have everything releasing its energy simultaneously.
Yeah, so methanol in a pre-ignition sort of situation, detonation is slightly different because you still have a frame front, but the methanol is giving off all that heat basically at the same time. All the molecules can burn at the same time. But from the point of view of preignition, it's like bombs going off in there, or a flamethrower effect. It's much more damaging on the engine structure. And as I said, our data indicates it happens very quickly. We can have normal combustion, and then 100 engine cycles later, which is round about, it's a 4-cycle engine, but it's a second later, you've got a hole right through the piston, and you can't react to it. It just happens that quick.
I think the point you've made there is one that's really easy to overlook. I mean, everyone goes on about the benefits of E85, particularly with its resistance to knock. And the same goes for methanol. They're very, very resistant to detonation occurring. But it's easy to overlook that these two fuels, in comparison to pump gas, are also more prone to pre-ignition occurring. So I think it's worth just dwelling on that for a moment, because it isn't common knowledge, I don't think.
No, and pump gas is a mixture of a whole wide range of hydrocarbons. Compared to, you can get pre-ignition on the petrols, but it's not the same as the alcohol fuels, because those different carbon chains are all different lengths, so they're going off at slightly different times and sort of cushioning the effect to some extent. So,
that being said, I mean, this is a real concern in the OE world, with this sort of drive to downsize engine capacities and introduce sort of small capacity turbocharged direct injected engines in terms of improving power density and emissions efficiency. The downside is that the OEs are experiencing, and sort of continue, as I understand it, to research low-speed pre-ignition in these gasoline-based engines. Is there a similar... What can we learn, I guess, is the question here, from the OEs in these direct-injected small-capacity engines? Is the failure mode and the causes for pre-ignition in those applications comparable or similar to what you're finding in these high-boost methanol drag engines, or are they two completely different animals?
Well, I think the OEMs... the ones which were involved in Formula One in the 1980s were exposed to these essentially super knock events, but these pre-ignitions, because I used to see them on TV in those BMW engines, for example, during qualifying, where they'd run the holes through the pistons and trail that smoke out. But then they would have dropped that line of research and development for a number of years, because the factory engines just don't reach these cylinder pressures to initiate some of these more extreme super knock or pre-ignition events, up until, as it turns out, the development of these direct injected engines, where they're downsizing, they're trying to improve their emissions. And the emissions improvement is a great way to stay away from pre-ignition, because as it turns out, when the OEMs turn their attention to this low-speed pre-ignition phenomena in their direct injected engines, they found out the main contributors was fuel impingement onto the cylinder walls, and actually mixing with the oil film, and essentially an oil dilution problem with the fuel, lowering the ignition point of the fuel to the point where the spark plug can actually light it off. And even then, in that situation, it was what we call, as the scientist in me tells me, it's a stochastic event. It's a relatively random event, but when it does happen, it's actually extremely damaging to the engine structure, which is why the OEMs, and we're talking fairly recently now, from 2005 to 2010, 2012 was when a lot of the SAE papers on pre-ignition in these direct injected engines were actually published. And I guess in part from my background in science, in the marine sciences, I have actual access, library access to these papers. And that's what that's how I was learning about this problem that was afflicting our dragster, and what I may or may not be able to do about it to fix it.
Okay, so what could be taken from the OE's research and applied to what you're seeing, and what is obviously a dramatically different specific application there? Is it the same situation where we're seeing this dilution of the methanol fuel by oil on the cylinder walls? I mean, obviously it's made worse, as you alluded to earlier, because we're running such rich air-fuel ratios. We're pouring, I mean, first of all, you're dealing with the stoic air-fuel ratio of methanol 6.4 to 1 versus 14.7 to 1. So even all other things being equal, we're simply pouring more fuel into the engine anyway for a given mass of air. And then on top of this, we also typically run on methanol much, much richer anyway, as you sort of mentioned. Is that kind of one of the key drivers here of just this oil dilution of the fuel?
Well, I can't talk about any other type of engines at this horsepower level. 60 pounds of boost is where we ended up. But for our FJ20, that the fueling is definitely a major contributing factor, but it also inherently went back to the inherent design of the cylinder head and how it affects things like mixture preparation, fuel vaporization, and all these other issues that impinge on how big your chances are of having that fuel mixing with the oil on the cylinder wall and pushing across the warm spark plug to start this pre-ignition process. So it's like in the modern engines, you may not necessarily see what we see in our old FJ20 engine because the engineers in through the 90s and the noughties, they weren't standing still. They were engineering a lot of these issues out of these engines that a lot of people are playing with today because of the move towards reducing fuel consumption, improving emissions, and all those other designer factors involving around burning what fuel you have in the chamber.
Plus, of course, they've at this stage got the benefit of CFD and the likes coming online, so they can actually go through sort of iterations of designs and see a direction that's actually going to give them the improvement they're looking for, correct?
Absolutely. And this is what we didn't know when we went along this journey with the older engine, is that CFD and that they haven't been sitting on their hands doing nothing during this time. That stuff works. Anything you can do to reduce fuel impinging on the cylinder wall or being caught in the crevice volume at the top of the piston, you can't burn that stuff there. It's in the boundary layer. What they've been working on this past 20, 30 years is getting that fuel away from those areas, those stagnant areas of the chamber, into the center of the chamber, in around the spark plug, so that you can burn it. If you're burning that fuel and getting it towards the center of the chamber, it can't cause mischief at the edges of the, on the cylinder wall or mix with the oil there. So a lot of these issues just don't exist in the modern engine, or if they do, they exist at much higher specific power outputs than we were at, because essentially what the boost does, what I found during that whole development process, the boost exaggerates the inherent underlying issues in relation to mixture preparation and actually burning these air fuel mixers, which of course Nissan didn't have to deal with in early 1980 when they're developing a World Rally engine, which wasn't even emissions compliant.
You've used that term mixture preparation a number of times, so let's just dive into this. I mean, it should be relatively self-explanatory, but what are we trying to achieve with this mixture preparation? Is it a case of a homogeneous air-fuel mixture? And by that term, I'm simply meaning that throughout the combustion chamber, our air-fuel ratio remains the same. I mean, that would be an assumption I think most people would make, but of course that's not always going to be the case. We're going to probably have richer areas and leaner areas inside of the combustion chamber. So is that what we're trying to do in terms of optimal mixture preparation? Does it also come down to how the fuel is introduced in terms of whether it's introduced as an atomized liquid or a vapor? And then the other element that you've kind of referred to there, is it about preparing that mixture so it's as close to the spark plug as we can get it without being diluted around the outsides of the combustion chamber where, as you mentioned, sort of it can get up to mischief?
Absolutely right. All of those things.
All of the things, okay.
And once you start thinking about it, it's a whole new appreciation to how the port shape guides that fuel into the cylinder, the relationship of the valves, the piston top design, obviously working even further back, the injector size, type, orientation, whether it walls the fuel into the port or into the actual runner, which I think was one of the problems that we had with our installation in the dragster, is we were walling some of that fuel. Our data show we had some of the larger Moran atomizer injectors there for a while that we tried, and the engine really exacerbated our problems a bit. They were quite a very broad spray designed for a big block Chevy, something like that. But we were trying them because they were quite a big injector and we had quite high fuel flow.
It gets difficult when you're running on methanol because the sheer volume of fuel you need, specifically when you're making the sort of power numbers you're talking about or north of that, there's not a huge selection of injectors on the market that are up to the task, really. So you sort of pigeonholed a little bit into using what is available. Now, the other element as well with the methanol fuel is that it's got, as you mentioned, a high heat of vaporization, which simply means as it goes through its phase change from liquid to vapor, it's absorbing a lot of energy out of the combustion charge in terms of heat. So it's got a massive cooling effect. Can that in and of itself become problematic with the fuel wanting to wet out on the cylinder walls, etc.?
Well, certainly yes. If you're trying a direct injection, of course, exaggerates that even further because you're injecting it into the chamber. But if you're port injecting on the back of the valves, it actually has very little time to vaporize. If you have liquid fuel in the chamber, that's where your risk runs for these sort of things, because you'll provide that opportunity for that oil to mix with the liquid, which is what the problem we were having. But in the end, we found that indeed this was the issue with this particular platform, because the further away from the cylinder that we injected methanol, the better it went. We ended up removing the intercooler. That was actually one of the big jumps in performance that we had, is keeping extra heat in the intake charge right up to the level of the port. And it made a big jump doing that because we had relatively poor combustion characteristics, which made me think, well, a lot of those Chevy guys for a number of years running those things that they were running, they didn't need or probably want intercooling for a lot of those things, probably because of this same effect.
So essentially, you're actually using the heat produced through compressing air through the turbo to actually bring up the inlet air temperature and help that fuel when it is injected to vaporize, as opposed to cooling down that inlet charge temperature with the intercooler?
Yeah, well, we glossed over quite a few things.
Absolutely.
in relation to this dragster, but it's I guess I'm a bit of a mad scientist, and Jeff was very keen. We had a fully instrumented engine. We started with an intercooler, a dry ice intercooler. We could get our intake temperatures below zero. It didn't like that at all.
So it's sort of almost completely counterintuitive to everything we learn when we're developing gasoline-based turbocharged engines, correct?
Well, and again, and this, I guess, is a great learning curve for me, but probably for others listening as well. What you read on the internet and how it relates to what you're actually doing, even what you read in a book, and what your actual installation and what you're actually doing at the time may be completely different. A lot of these things we arrived at based on first principles, reading spark plugs, obviously looking at your data for sure, but going back to actual physics principles on what that fuel's doing and how can we best get this thing to go down the track. Because in the end, we end up using some tricks that were developed during World War II, during the piston engine aircraft in those times, in relation to injecting methanol before the compressor. It's something that you see very few turbo cars do. This neck of the woods is very common in top alcohol drag racing. It makes the compressors more efficient.
Yeah, I've never experimented it with myself, but I have read about it, and yeah, that was my take on it, was it helps improve the compressor efficiency. Just coming back to the intercooling element, because I have struggled to really get solid results, I guess, from people who have experimented both with and without intercoolers. When I developed my own Evo, we kept the intercooler because for me it was a known quantity. And as I sort of went through this, we never removed it to test, and maybe that's one of the things I kind of regret now. But obviously you want the intercooler because we create huge amounts of inlet temperature when we're running 50 plus PSI of boost. I mean, it's physics. We have to create heat when we compress air. Obviously heat is the enemy of power, but when we're measuring the temperature coming out of the turbocharger, that's one thing. But with methanol fuel specifically, because again the latent heat of vaporization and the sheer quantity of fuel we're injecting, when we're actually, it would be difficult, if not impossible, to accurately measure, but what it's actually doing in terms of charge temperature inside of the cylinder is going to be quite dramatically different compared to running a gasoline engine non-intercooled. Am I right on that sort of thinking, that the methanol we can get away with that lack of intercooling because of the fuel's properties?
Well, it's funny you said that it's impossible to measure. Maybe on the other side of the inlet valve, mind you, the OEMs with their development of these direct injected engines, they do all of that with their combustion analysis and combustion pressure stuff. For us, we actually had data instrumenting the engine for inlet air temp based on how much fuel we could inject upstream of the inlet air temperature sensor. And you can work out, the mathematics for that type of thing. I can do that sort of maths relatively easily. And it was actually as per you would work out mathematically the temperature drop that you would get. So if you've got a good idea of your horsepower that you're producing and the airflow required for that, even either through the compressor map or the ET of the car, mile an hour of the car, and based on your airflow and your inlet air temperature that you start with, you've got a fair idea of the mass of air that you have to cool down. And based on the latent heat of vaporization of the methanol, you can do your calculation, work out how much methanol needs to be injected to get the temperature down to a certain level. Go add that. We were using a mechanical injector for that. Go do the calculation on that, put that fuel in and find that the inlet air temperature did indeed drop to the temperature that you calculated.
Right. The physics doesn't lie.
Well, yeah, the physics is what drives these engines. These engines, internal combustion engine, its purpose is to convert chemical energy into mechanical energy in the form of a rotational force at the output shaft. And combustion is the chemical reaction. The physics is absolutely driving that process, which is why they can model it through CFD.
Just coming back for a moment to the vaporization of the fuel and how it wets out on the port wall. This is something we're going to see in absolutely any engine. I think there's a misconception that the fuel is injected and beautifully atomized by the injector and it enters the cylinder when the intake valves are open. Of course, obviously it does enter when the intake valves are open, but there's only a relatively small portion of the complete engine cycle when the intake valve is open. So most of the time when we're at high RPM and higher load, we're going to be spraying at least some of the fuel against a closed intake valve. But when your engine's at operating temperature, the back of the valve's hot, the inlet port is hot, so the fuel tends to go through that phase change into a vapor. So when the valve opens, it's then introduced. So that's great. That's really what we want, because vaporized fuel is much, much easier, magnitude easier to combust than liquid fuel, no matter how well it's atomized. The problem I see with a drag engine, particularly one that is a dry deck, you've got no coolant. You can't sort of warm the thing up for 20 minutes in the staging lanes before a run. There's a limit to how much heat you can get into the engine before you risk it overheating. So does this become problematic as well with this aim of trying to vaporize what fuel does end up stuck behind the valve?
Well, yeah, if you understand these things and start thinking about what you're trying to do, these things are absolutely critical. So we were always very careful about warming up the engine and making sure we had a minimum amount of heat in the thing. But on the point of view, obviously you can overcook it. And at the end of the day, so the other thing at this level of tune is for an FJ20, there's no coolant in the head, right? So it's actually solid fill the head as well. And we arrived at that we cracked some of the heads due to abnormal combustion and still wanted to use them. So just fill them and away you go. And then you found, this is actually we can run this way provided you don't exceed a certain critical temperature of your spark plug. But at the same time, once you learn about this pre-ignition phenomenon, you need to be able to vaporize that fuel and have a minimum amount of temperature in the heat structure, temperature in the engine structure to actually do what you're wanting to do. So it's a mixture, it's a cross between a balancing act on a stick of dynamite with a certain length fuse.
Yeah, okay.
So you have a certain length fuse. The methanol gives you a longer length of fuse than, say, for example, if you've looked at some of the engine data from a nitromethane burning engine, where once you get beyond a certain percentage of nitro that you're burning, the EGTs won't level out during a run. They keep rising. So that's a certain length of fuse that you have to get the job done based on the amount of fuel, because nitro is carrying all of its basically as oxidizer with it. You add more nitro, you can't cool it down. You're actually adding more fuel to the fire. So that's what the EGT is on the nitro engine. So the methanol you can put enough fuel in there under normal combustion to stop that from happening. And indeed, you can quench that EGT and lower them over time. But then the more unburnt fuel in there, the higher your risk of this pre-ignition, in which case it sweeps around completely, in which case you're adding more fuel to a fire that's already in there. So you're playing with fire.
So more fuel's great to a point, but then when you're starting to get these abnormal combustion events, more fuel is really actually the enemy.
Well, yeah, we end up burning through, say, a JE piston just faster.
Yeah, okay, not ideal. All right, the other element in terms of the mixture preparation during the compression stroke comes down to the combustion chamber design, shape, etc. And I'm interested to dive into a topic that seems to have divided opinion, which is squish pads would be the term that I think we should use here. Again, difficult without the benefit of pictures here, but most people are going to probably be able to Google what that would look like in terms of the combustion chamber shape. And when it comes to building high RPM, high boost drag engines or performance engines for that matter, a lot of people will machine out or hand port out these squish pads and remove them from the combustion chamber. Can you give us your sort of perspective on what these are actually designed to do in an OE application and why they may be not ideal for our purposes?
Yeah, certainly. Well, the FJ20, first of all, it has relatively large flat squish pads there on each side of as I mentioned earlier, a pent roof combustion chamber with quite a wide included valve angle. This is not ideal for providing stable combustion at high boost. And I guess a lot of these things based on our experience and what I've learnt from your stuff, Andre, and speaking to others in the Sport Compact, where the brake mean effective pressure or the BMEP or specific horsepower output above which this stuff really becomes important is around, the BMEP is around 800 PSI, around 9 to 10 horsepower per cubic inch, or about high 500s to 600 horsepower per litre. All this stuff becomes absolutely critical, the combustion chamber shape, design, and the mixture preparation, which of course also includes the port shape. So based on the FJ20, all this stuff was exaggerated. We had a round port, which provides relatively little tumble effect. Tumble is sort of over the falls effect as it goes through the valve. So the in-cylinder mixing is not as high as a later model head. We have a large squish pad. In our case, we needed a certain amount of compression ratio so that we could have a certain amount of bottom end torque to get the thing up on boost. So we ended up with a flat piston top. That's not a good idea for these earlier engines, the flat piston top, because we're activating all of that squish area. Point of view, that last bit of the cylinder rises towards TDC on the combustion stroke. That's providing, and especially at the high boost, excessive turbulence.
Okay.
The squish is designed, I think, to waken up that last part of the combustion cycle at low speed in engines with relatively low specific horsepower outputs, like your street engines.
So we're trying there to kind of move the mixture from the outside of the combustion chamber in towards the spark plug, correct? That's the intention of the squish pads?
Well, yeah, and also it's your final stage of mixture preparation, isn't it? So there's a whole range of other things that have occurred up into those last, say, 30 degrees of movement of the engine up towards TDC.
I mean, this is sounding, however, like what we would want to achieve. You know, we've talked about the wall wetting of the fuel and the oil dilution. Obviously, that's going to happen if we've got fuel sitting out there on the cylinder walls. Getting that fuel air mixture trapped in that crevice volume, basically between the top ringland and the cylinder wall where it can't burn. So, I mean, everything so far is sounding like these squish pads are probably going to help. Is the problem come in when you combine that with now a flat top piston as opposed to the factory dish style piston, or is it more along the lines of what works in a factory application between 2,000 and 6,500 RPM is very different to what we want with 60 pound of boost on board and 10,000 RPM?
Yeah, well, it's the latter one. We're forcing this platform to do something it wasn't designed to do. We're moving things in certain ways. We're adding a lot more fuel to the chamber. The port shape is still basically the same. So we're arriving with a situation as that piston comes up where the fuel isn't all homogenized There's probably rich pockets. The crevices is one area. And what that squish is doing is actually preventing access to burning that stuff in those back corners of that combustion chamber, while a more open chamber or a slant type squish area, things like Ecotec, I think, is one engine where they actually open up that chamber and narrow the included valve angle. It provides a much better opportunity to burn more of the fuel and that's available. And this is one of the things, if you put an FJ20 on, I guess, an emissions rig, and an engine manufacturer or a car manufacturer went and tested that, it would fail the modern emissions, because you have these areas of the combustion chamber, probably even at their factory, 2,000, 6,000 RPM. They're not getting a complete burn in those areas. So all we're doing is exaggerating that with 10,000 RPM and 60 pounds of boost. And so when we exaggerate a problem, we just get bigger problems.
Yeah, definitely. If we look at the engines that are currently successful in the world of sport compact drag racing, I mean, they all, for the most part, are a relatively old design, albeit admittedly not maybe quite as old as the FJ20. But I'm thinking here we've got obviously the Toyota 2JZ, there's the Nissan RB26, obviously my favourite, the 4G63, and Honda's B Series and K Series as well have all shown high levels of success. What is different about the design of these combustion chambers that makes them live, or do they still require the same redevelopment in terms of getting them to work at high boost with methanol fuel?
To be fair, I haven't run those other engines at any high specific horsepower level. We have had some experience. Again, it's probably a good time to probably chat about it. In the end, with our dragster, Jeff, once we decided we'd reached the end of the FJ20, he went and actually engineered a K24 Honda engine in there. So we basically went 20, 25 years further down the line in engine development.
Yeah.
That Honda, it would boost without nitrous. This is the same car, same transmission, same converter. Didn't need nitrous to boost up because you could boost it up on the smaller cam. The VTEC was fantastic that way. And by all accounts, he told me it made about the same, at lower boost. We didn't run it at the really high boost, but it made the same horsepower as the FJ20 with 10 to 15 pounds less boost. That's what engine development is.
You're probably also comparing what we could argue is probably one of the best cylinder heads of modern times, correct, with that K-Series head. They're a pretty special engine all round, realistically.
But that's what we're talking about, aren't we? What is in that cylinder head that makes it so good? And it's not just the extra 200 cc's or 300 cc's of capacity. I think in the end we were nearly 2.1. He's 2.4. So that can explain some of the bottom end extra torque. But these modern cylinder heads, they are better. And that cylinder head combustion chamber and port design of that K-Series has been developed to optimize fuel economy, minimize wasting the fuel and maximise horsepower. And that's where we've gone in this past 20, 25 years.
So hence you're getting superior mixture preparation.
And the other thing you're getting is stable combustion. So when you go to 60, 70, 80, and now even 100 pounds of boost, some of these guys are getting to now, the combustion's remaining stable because that port and the injectors, positioning and other things, and the in-cylinder motion of that fuel air charge during the mixture preparation phase is providing, as that piston comes up that last 30 degrees before TDC on the combustion stroke, it's providing a much more homogeneous, better controlled air fuel charge to be lit off by that spark plug, which of course greatly reduces your chances of these pre-ignitions and these other abnormal combustion events. So that they're just better. They've built a better mousetrap.
Does it get to a point though, the current crop of performance engines, the current crop of modern engines, I suppose I should say, we've sort of seen this constant trend towards downsizing capacity, and direct injection obviously is the way forward with OEs to meet emissions and efficiency targets. And I'm sort of seeing, if you look at the latest generation of turbocharged K20 factory engines, they've got the turbocharger now bolted directly to the cylinder head. Obviously, it's nothing new in terms of an OE technology, but obviously that works well when everything is designed around a specific power target. Let's say that's 300 horsepower, for example. But then when we want to take that new generation engine and modify it to make 1400, often that's just going to simply be impossible. There's no way to port that head to that level. So have we sort of gone through, in your opinion, the sweet spot of these engines that we could modify to that level and we're never going to see again?
Well, if you think about the development, what was it, 1880, I think, Carl Benz, internal combustion engine in that time, they've polished a turd, what it's essentially a turd. These things, spinning around, producing little explosions that push a piston down, and eventually we hope to get some torque out the back. They've polished that turd to a really fine finish. These are highly developed engines that we're playing with nowadays. Even the ones that are 10, 15 years old are extremely efficient. The brake-specific fuel consumption and everything's very low.
They've polished the turd and then rolled it in glitter as well.
Exactly. And so what you mentioned there is emissions. So when we talk about things like Dieselgate, I mean, VW, their engineers drove that. How do you get a better fuel economy out of a VW diesel? Well, you run it leaner. That reduces your CO2. But the problem with combustion is that if you reduce CO2 and have excess oxygen left in the exhaust, it combines with the nitrogen and forms oxides of nitrogen.
NOx outputs go through the roof.
And then that's photochemical smog. I mean, this combustion process, in the end, is the limitation of these things, which is why we are seeing emissions is what's driving this move towards electric vehicles, because electric vehicles are another way of converting chemical energy into mechanical energy. From the point of efficiency,
they do it with far, far superior efficiency.
Yeah, they're not trying to do it via a piston or a valve, but the internal combustion engine is never going to be able to meet that same level of efficiency. And these are the same sort of things where we saw, I mean, in 1945, most combat aircraft were piston engined, except for the Me-262 that the Germans produced, and there were a few prototypes that the Allies had. But how many piston engine aircraft do you see nowadays flying us around, say, between Brisbane and Queenstown? There's none.
Yeah, no, it's not going to be a thing for sure. I mean, I think the writings are firmly on the wall. I mean, I think that the numbers, if obviously it's very dependent on the engine, but numbers sort of normally thrown around for internal combustion, sort of 35% efficient. Maybe if you get up to F1, I think they might have hit about 50%. And from what I understand, EV, you're sort of in the low 90s. So it's not even a competition, correct?
Well, it's low 90s almost from the point of view of getting the electricity in the car. The actual electric motors are up 96%. 97%. Like these things, they're actually, from the point of view of rotating, getting a rotational force at the output shaft, they're a better mousetrap. The only issue in the short term with the EVs, getting the energy out of them doesn't seem to be a problem. If you look at a Rimac or a Tesla Plaid, you buy a £4,000 four-door family saloon runs 920s for the quarter. And if and I think 7 minutes 25 the other day around Nürburgring. Think about that 10 minutes ago. And then we've got the sports car, which is the Rimac Nevera, 8.2s, 180. Charge it at home with your solar.
Yeah, I was talking to a friend about that a while ago, and this is a car with, obviously, if you've got the financial resources, that you can buy off the showroom floor, that runs as fast as my drag car did. But I mean, my drag car required a complete engine rebuild every 6 kilometres. You certainly weren't driving that to and from work, and nor were you driving it through the McDonald's drive-through. It is wild to see how far that technology has come. However, I think we could probably have a completely separate podcast, and maybe we should, on the EV technology and the state of that, because I know that you are a massive advocate for it. However, I think we've well and truly broken our current record for the longest podcast episode, and I think with respect to your time, we will move towards wrapping this thing up, Ben. And to do so, we've got the same 3 questions we ask all of our guests, and Again, you're a slightly unique guest here in that your actual occupation is not in the automotive industry. So we'll see how we can tweak these towards your unique situation. The first question we have is what's next in the future for you?
Oh, I think we just touched on that. I've got 2 teenage kids here. They've got their licenses and their first cars. They're running little Honda. Matthews runs a little Honda K-Series in a Civic VTEC, and Jamie has one of the little 2ZZ Celicas. These are great little motors. These are really well-developed things. I've told them I'm more than happy to play with those or build another car for them if they want an internal combustion engine car. However, at the same time, I did develop an electric go-kart for them. I must admit, I have moved over to the dark side in some respects. I've bought a Tesla Model 3 Performance, and that's been a fantastic car. Actually, we're 100,000 Ks in. We charge it mostly with solar, but we charge this go-kart with solar as well. And as you probably gathered, even though I'm a hobbyist, I do like to know how my wheels work and what gets me around. So to learn about EVs, I built a little electric go-kart, and it was 80 volts, lithium ion, 300 amp batteries, 80 volts by 300 amps is 24 kilowatts in this little go-kart, and the kids love it. It does 122 kilometers an hour by GPS down the road, and we have fun with it.
Yeah, that'd be enough to have fun with for sure.
Yeah, well, they love it. There's no maintenance. I think we oil the chain. And that's 6 or 7 years now. So I could see in the long term, once we get some aftermarket support for these EVs, or say better batteries for your Tesla or a cheaper, lighter battery, I could see myself doing something like that, because even though the Tesla, the Model 3 Performance, I like it. I've been doing some sort of hill climbs and carnacross with it. It's really fast. The center of gravity, it's so low. But that's the thing with these EVs. It's such a step change. It's a truly disruptive change in automotive, because I looked at doing an EV conversion on my old Datsun, but I ended up selling it because you couldn't get the batteries in the right places. You would have ruined the car. The polar moment of inertia would have been terrible. You need these skateboard platforms with the battery in the middle, in between the wheelbase, and your engines up front and rear. I mean, that's a superior way forward for a vehicle. It gives you more room inside and all these other things. So we've got to sort of wait for a bit of a trickle down for the aftermarket to be able to come and cater for all these vehicles. So I guess that's, in the future, that's what I'm waiting for. But in short term, I'm enjoying the Tesla, and I'm waiting for the kids to tell me they want to go fast, and then we can go fast.
Yeah. I mean, just to be super clear, we're at HPA definitely not against EVs. I do still like my internal combustion engines, but we were shopping for a family car just late last year, and I was trying really hard to find something that fit the bill that was full EV. Unfortunately, with 2 kids and a requirement for 7 seats, that really narrowed the choices dramatically. So it wasn't quite an option then. We're also working on an EV course, which hopefully will be out probably, I would say, early 2024. So it's still a little ways off if you're listening to this podcast as it's just coming out, but we've partnered with Sasha from Mountain Pass Performance in order to develop that course. I think the technology is so exciting because it is advancing so quickly. And in Sasha's point, if you looked at the ludicrous mode Tesla that was out a few years ago, and really that was developed to allow magazines to go and do a super fast quarter mile, and that was about it, because it would start derating after that because of the heat that was produced, versus now the Model S Plaid, and it can do several laps around a racetrack at relatively close to its maximum output. So it's so early in the development of this technology realistically that it's super exciting to see where this will go. More importantly, I think, at least as far as our course development goes as well, I think you're going to start seeing more and more access to affordable aftermarket componentry or EV swap componentry to make this more accessible to the enthusiast, and that really excites us. We're pretty keen to do our own in-house EV project at some point in the not too distant future.
Yeah, no, that's really good forward-thinking stuff, mate, because when you look at this transition to EVs, it's some people seem to be in denial, but the reasons that people are switching over are actually sound engineering reasons. Some of them are economic reasons, but it's very similar to that transition I think I mentioned from piston engine aircraft to jets. I mean, they're simpler, they're more efficient, and they do the job. And for the majority of people, probably not the listeners of this podcast, they want something like their phone. They want their car to be like their phone. Next time I saw my first car the other day, I checked over for a friend where you pull the dipstick out and there's no oil on that sucker, right? So, a lot of people...
Maintenance less of an issue with the EV platform for sure.
Well, a lot of people just want an appliance, and the EVs are an appliance. Some say they're boring. No one who opts in my Model 3 Performance thinks it's boring. I actually would like an extra couple of hundred horsepower, and I think it's great that you're partnering with Mountain Pass and Sasha. He's doing some fantastic work. I have some of his suspension on my car, and we're sort of mentioned a couple of times. I'd like 700 horsepower in my thing. The Plaid's just that next size bigger platform, but something like that. We're talking about streetable, daily driver, 1,000 horsepower cars that sit in traffic. And actually with EVs, the slower you go, the more efficient they are. So they are actually the future.
Yeah, I don't think there'd be too many doubters there. I'll be keen to put my hand up and say I'm definitely going to miss the soundtrack of a internal combustion engine, but that's a different topic for a different day.
There'll be our weekend rides, mate.
Absolutely.
During the week, drudgery is what the EV's for. I think Jay Leno's on record to say, and he's right. Jay knows his cars. The car freed up the horse for weekend recreation. So that's what EVs will do to our combustion cars.
All right, next question, Ben. Is there any advice you'd give to a younger version of yourself or one of our listeners? And this one is a bit tricky because I'm not too sure how many of our listeners are sort of looking for a degree in microbiology, but let's see how we can adapt this. But any advice you'd give to a younger version of yourself to help reach where you are in your career faster or maybe avoid some pitfalls?
Well, I did have one, again, with the Tesla. I shouldn't have sold those shares as early as I did. That would have made a killer. But essentially, guess less is something that I've come up with. Like if something comes up in an area that you're working on or an area you're interested in, don't guess, learn. That's what courses like HP Academy are all about. I mean, I learnt a lot of this stuff with internal combustion. It's not my day-to-day job. I learnt because I wanted to know, and I bought books and I read stuff. You do the maths. These things are basically miracles of modern science. Chemistry, physics, mathematics all combine, all together in an internal combustion car. So you can learn as much as you want to learn about them. So I encourage people to learn and guess less.
I think you're absolutely on point there. I think there's this common belief or mistake being made in the automotive aftermarket industry that you're trying to fix a problem and you have to fix that from scratch, and no one else has ever seen that problem before. The reality is none of this is new, and probably if you're facing an issue, hundreds if not thousands of people have seen the same issue, and you're going to fast track your progress, get a better result, and probably undoubtedly save time and money by actually figuring out what other people have done to rectify that situation. And particularly your angle, I think, comes from that sort of tertiary education that you've experienced, in that you're looking at white papers that OE manufacturers have produced showing their research. So you don't have to go to the trouble of replicating that research, which would be, for the average individual, essentially impossible anyway. All of this information, what I'm getting at, is really out there. It's just a case of actually getting off your ass and putting in the work to find it.
Well, in the modern world, the education system should be, and if it doesn't, it should be giving you the skills to be able to sort out the information from the misinformation, right? And that is it's a real skill. And so you bring that ability or learn that ability, and this is what I hope further education is providing, is that skill to, organize skepticism is something that we talk about as scientists, but that ability to deconstruct what you're looking at and bring it back to the fundamentals. And if you're talking about engines or any mechanical device, the fundamentals are the physics. behind how it runs. The physics and the engineering is what drives these things. So if you really want to learn about them at more than a superficial level, they are the things that you need to learn about.
Absolutely. Could not agree more. All right, Ben, last question for today. And again, this is a bit of an odd one for your particular situation, but let's see how you can work with it. If people want to learn more about you, find out what you're up to, or maybe they've got sick fish in an aquarium, how are they best to reach out?
Yeah, well, I guess the best way is to have a look at my business website. I think it was made by one of your mates, Andre, 20 odd years ago for the price of a carton of beer, but now the kids tell me it's retro.
It's retro for sure.
Retro cool, digsfish.com. There's some stuff there on EVs that I actually presented to some scientists at a conference that might interest some of the readers, because it does link some of the reasons for this transition back into things that perhaps some of the listeners may not be familiar about in relation to environment. There are other reasons why we are moving towards these EVs, and there are some compelling environmental reasons why it's probably a good idea to do it sooner rather than later. So if anything, I am building engines for people still at the moment. Those bluebirds that we talked about at the start, those are groundbreaking bluebirds. I build their engines now. I guess interesting projects. I'm happy to look at them anyway. No guarantee I'd take any on. But I prefer to leave a lot of that automotive stuff to the true professionals, the experts like yourselves there. You guys are doing a wonderful job. And I think it's, for the listeners out there, I knew this young fella, Andre, in New Zealand. I met him. He was working in a small garage down the bottom of Nowronga Gorge. And he was just like you today back then. But this young fella, Andre, he wanted to learn about what he was doing. He had an idea. He had great parents who supported him. And I remember him mentioning to me that he said, it's just crazy that I can't learn about this stuff. Where do I learn about this stuff? Well, Andre, you learn about this stuff from you, mate. You're giving all these people around the world that opportunity that you didn't have. And I just say, congratulations. Well done.
I appreciate it. We are certainly trying, and I think from the feedback we get, generally we're getting more hits than misses. So we'll keep on going. All right, really appreciate your time today, Ben. You've been very generous with us. Huge amount of information, very, very tech heavy. I know this episode won't be for everyone, but for those who have enjoyed it, I'd urge you to go back, rewind and have another listen. There's a lot of information in there to digest, and you're probably not going to get it on the first run through. So again, Ben, thank you very much for your time. We really do appreciate it.
No, thanks, Andre. It's an honour.
If you've enjoyed this episode of Tune In with Ben, we'd love it if you could drop a review on your chosen podcasting platform. These reviews really help us to grow our audience, and that in turn helps us to continue to get more high quality guests. To say thanks, each week we'll be picking a random reviewer and sending them out an HPA t-shirt free of charge anywhere in the world. This is also a great place to ask any questions you might have too, and I'll do my best to answer them if your review gets picked. So this week, a big shout out to Vader9 from the United States, who has said, best technical automotive podcast out there. I learned something new that I can apply to my 240 SX project with every episode I listen to. There is so much great content packed into each episode. Thank you, HP Academy, for doing what you do. Well, you're absolutely welcome, Vader. Great to hear that you are enjoying the podcast. And if you want to get in touch with your t-shirt size and shipping details, we'll get a fresh tee shipped straight out to you. All right, that concludes our interview. And before we sign off, I just wanted to mention, for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school, and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.